Night falls across the inner mind like a curtain drawn by a careful hand, and in that quiet, a shoal of distant planets begins to gather. Each one circles its star, with a patience that outlives mountains, cities, and the long memory of oceans. Their courses are steady, their rhythms slow, and their light arrives in small, regular sips. The cosmos holds many storms, yet here the attention rests on the tender things that last. An orbit is a lullaby written by gravity, and throughout the galaxy millions of such songs are sung. The stars pulse, the planets listen, and nothing hurries. Consider the way a planet moves, when no crowding force clutters its path. It follows an ellipse that repeats like a breath. Closest approach, gentle retreat, again and again, with the certainty of a heart that knows its pace. This repetition is not monotony, it is the foundation upon which temperate days can rise. The quiet fact is this: stability is common. In the mathematics of motion, most arrangements that survive their first noisy youth settle into calm. Small eccentricities round out over time. Tilts find modest angles. A world that keeps its promise to return gives its star the chance to warm it evenly, and a long sequence of mornings can unfold. There is a comfort in the scales involved. Years can stretch to lengths that humble imagination. A Neptune-sized planet far from its sun may take centuries to complete a single loop. Nothing breaks, nothing strains. The shadows it casts across the interstellar dark move with a dignity that soothes. Even on tighter tracks, the story can be serene. Some planets share timing with companions in simple ratios, 2 orbits here for 3 orbits there. They pass one another like lanterns on a shore road, never colliding, always keeping a respectful distance. This is what gravity writes when left alone with enough time, a choreography that avoids the sharp edge of chance. The light itself participates in the calm. Starlight travels as a steady river of photons, and when a planet slips between star and observer, the brightness fades by a fraction that repeats with clock-like fidelity. That repeating dip is soft to the eye and softer to the mind, a reminder that even at scales beyond any map, the universe can be measured with gentle signatures. Imagine a world sliding into view, then out again, a clean heartbeat on a graph, and then another and another. There is no shout here, only the most delicate nod that a planet is present, enduring, faithful to its line. Some stars are fiery and quick, but many glow with patient moderation. Their output drifts within narrow bounds, and planets respond with climates that evolve at the pace of continents. The air moves, clouds bloom and thin, but from year to year a listener would hear the same tone. Even worlds that turn slowly or lock one face to their sun can find balance. Along the twilight ring between day and night, winds run like quiet rivers. Heat slides from the bright side to the dark, smoothing extremes into long habits. A single star paints a permanent evening, and there, under a gradient that never quite ends, the sky keeps its color. Calm appears as well in the elemental recipes that planets prefer. Hydrogen, helium, oxygen, carbon, iron. Nothing excessive, nothing theatrical. The common materials of space assemble into spheres, and spheres prefer to rest. Gravity presses downward everywhere, and the surface answers with a curve that is the same in all directions. Even mountains, those sudden gestures of geology, erode toward roundness. Seas settle into level plains. Over time, that is almost too large to hold in thought. Craters soften, ash forests turn to stone, and stone returns to sand. The long arc favors the quiet state. There is a gentle, arithmetic, inhabitable distance. Too close, water spits into steam. Too far, it locks into ice. Between those fates lies a band that many stars can host. It is not a thin razor, but a generous lane where a planet can wander and remain temperate. The idea feels like a deep breath. Space is vast, and within that vastness, a broad region exists where mildness is not rare. Rivers may not run on most worlds, yet the conditions that permit rivers are not exotic. They are simply a matter of balance, and balance repeats. Even the unseen interiors contribute to the sense of ease. Cores cool slowly, mantles convect in gradual rolls. Magnetic fields, when they arise, can endure for eons, deflecting charged particles with a silent firmness. One could picture a planet wrapped in an invisible cloak, its surface spared the harsher music of its star. Nights stretch under a sky that does not crackle. Days pass without a constant hail of cosmic grit, and the long-term threads of atmosphere remain unbroken. The quiet is not empty. It is maintained by deep processes that do not boast. Time, the patient tailor, hemstitches orbits and climates with a steady hand. Disruptions do occur, yet the record of planetary systems shows a tendency toward order after the unrest of youth. Large impacts become rare. Leftover fragments are cleared or retired to distant belts. The surviving worlds rotate, revolve, precess, and nod in cycles that can be written, counted, and trusted. That trust is the softest comfort this story offers. If a listener closes the eyes and imagines a sky on a distant world, chances are high that the imagined dawn repeats on schedule. There is also the composure of numbers, hundreds of millions of stars in a single galaxy, each with some chance of hosting planets. The statistics grow like gardens when viewed from above. It becomes almost certain that tranquility is not a local specialty. Somewhere the nights are long and gentle, somewhere the afternoons last, tempered by a cool haze. Somewhere the wind is so slow that a feather could hang almost still for an hour. The mind does not need the exact address to feel the effect. Possibility itself is a calm climate. Instruments designed by careful hands turn toward this quiet and learn to listen. They do not demand fireworks, they value regularity. The smallest shift in a star's color tells of a planet's pull. A tiny change in timing whispers of another body further out. The faintest thermal signature hints at an atmosphere that holds heat the way a lake holds dusk. None of this is loud. The detectors sit in the dark and count. Each count is a pebble placed in a jar, and the filling of the jar becomes a song for sleep. At the edge of imagination, where the known meets the wished for, rests a gentle certainty. The cosmos is not only a theatre of violent births and spectacular ends, it is also a vast archive of continuities. Planetary paths that repeat, seasons that resemble last year's contours, tides that arrive, reflections that return to a small moonlit bay. The human mind responds to this cadence because it is built on cadence as well. Heart, breath, step, blink. To think of exoplanets is to join in a larger rhythm, one that began before any witness and will continue when witnesses are gone. Nothing needs to be fixed or conquered in this view. It is enough to sit within it and notice the unremarkable miracle of motion that does not falter. Worlds turn and keep turning. Stars shine and keep shining. The void between them holds its peace. Somewhere, a planet completes an orbit for the 10,000th time, and then once more. Somewhere, a moon rises to its smallest point and falls again. Somewhere night is a blue that has no word in any human language, and day arrives as a whisper along a line of distant hills. The universe has many voices. Tonight it chooses the softest one. They began with the gentlest of hints, a star's light shifting by a thread of color that only a careful spectrograph could sense. In 1992, an unusual signal emerged from the whirling remnants around a neutron star. Alexander Volshjan and Dale Frail traced slight irregularities in the pulses of PSR B1257+12 at Arecibo and found worlds circling a dead Sunday. It was an unexpected overture. Planets in a place no one had thought to search, revealed by the steady ticking of a stellar lighthouse. The method was clean and precise, a metronome revealing pebbles in the path, and it showed that planets could survive or reform even after catastrophe. A few years later, a more familiar star offered a quieter confirmation. In 1995, Michel Mayer and Didier Queloz watched the spectrum of 51 Pegasi at the Haute-Provence Observatory and saw it move in and out by only a few meters per second. That tiny sway implied a companion as big as Jupiter, hugging its star in a swift 4-day loop. The instrument measured the star's wobble with the patience of a watchmaker, and a new certainty entered astronomy. Planets could tug their suns with modest strength, and the tug could be weighed. The finding felt like a hand placed on a calm surface, sensing ripples that reveal the shape beneath. The first silhouettes arrived soon after. Astronomers noticed a recurring dip in the brightness of a star called HD 209458. In 1999, a gas giant passed in front of that star and dimmed it by 1%. and the transit told everyone that worlds could declare themselves with shadows alone. A curve of light became a ruler for planetary size. The duration of the dip set a scale for the orbit. With these facts, the outline of distant systems grew sharper. This was not a violent discovery. It was a quiet crossing, the kind a photographer might wait for at the edge of a lake, knowing the light will speak when a bird glides past the sunday. Precision matured in the next decade. The HARP spectrograph in Chile took to measuring stellar wobbles with accuracy near a meter per second. That is walking speed, applied not to a person, but to a star many light-years away. With these observations, small super-Earths stepped into view, their gravity recorded as barely audible notes in a spectrum. Each note carried mass, period, and a hint of orbital shape. The cumulative effect resembled a soft chorus, a layered harmony from countless suns. Then the field widened into a broad, quiet plain. In 2009, Kepler rose above the atmosphere and stared for years at one patch of sky in Cygnus and Lyra. It did not look for drama. It counted regular fades, as if counting tides. The mission returned thousands of candidates, each a gentle indentation in a star's glow. From these counts came the first reliable maps of planetary sizes and frequencies. Small, rocky bodies turned out to be common. Compact systems appeared where several worlds orbited closer than Mercury does, each tracing a narrow ring with tidy timing. This census gave a new kind of comfort, the comfort of statistics that point toward abundance. Along the way, atmospheres began to whisper. In 2002, sodium was seen in the air of HD 209458b when starlight filtered through its limb during transit. The signal was faint but repeatable, a single element speaking from many light-years away. Later, water vapor left its mark in infrared spectra on multiple hot Jupiters, and thermal phase curves revealed dayside heat shifting to nightside winds. The picture grew detailed without losing its calm. Layers, temperatures, molecules, all arriving as small corrections to models that stretched back to laboratories on Earth. Another quiet pathway opened with microlensing. When a foreground star drifted in front of a farther star, its gravity magnified the light and drew a smooth brightening. If a planet accompanied the lens, an additional soft spike appeared. Observers with patient schedules recorded these events and found planets far from their suns, even down to low masses. No photons came from the planets themselves. They were known by the curve of time, a passing shape in a light curve that would never repeat in exactly the same way. Even so, the effect carried a delicate authority, a fingerprint pressed in passing on a sheet of light. Direct imaging offered glimpses of worlds as points of their own. In 2008, the HR 8799 system yielded several bright companions in wide orbits, and Beta Pictoris revealed a planet close to its dusty ring. Coronagraphs dimmed the parent stars until planets shone like jewels at the edge of vision. The exposures ran long, data reduction was careful. At the end sat a speck where a speck should be, steady in frame after frame. To see a planet's own photons felt like a slow breath held and released with satisfaction. Transit timing variations added another layer. If a planet arrived early or late to its crossing, unseen neighbors could be inferred. Kepler's precise clocks allowed the detection of interlocking systems where gravity traded minutes between orbits. The method had a softness to it. No new dot appeared. Only the rhythm shifted, and from that shift emerged masses and mutual pulls. It was as if a pair of dancers off stage altered the tempo of a partner on stage, and the eye learned about the hidden steps by watching the visible footfall. Small stars gave generous hints. The TRAPPIST telescopes and Spitzer observations uncovered a family of Earth-sized planets around a cool red dwarf, packed within a range where water could take on liquid character. The transits were deep and frequent, ideal for study. Each pass etched a precise rectangle of dimming, and the sequence lined up with satisfying clarity. These were not distant gas giants alone. Rocky companions crowded close, offering targets where starlight through air might one day reveal the chemistry of a temperate sky. Ground-based arrays kept listening. Automated surveys learned the habit of night after night repetition. TESS began to sweep the full sky in sectors, finding bright stars with small planets that follow short paths. Follow-up networks coordinated like a quiet orchestra. Spectrographs weighed the discoveries. Photometers confirmed the shape of eclipses. The cycle of proposal and observation grew efficient without losing its gentle pace. Each object received a designation, a schedule of visits, a thin folder of light curves and velocities that amounted to a biography written in steady lines. With the arrival of a new observatory in deep space, exoplanet atmospheres became more articulate. Spectra of warm gas giants showed carbon dioxide with unmistakable structure. Sodium and potassium appeared with clean edges. A scattering slope rose in blue, consistent with haze made of fine particles. Thermal maps traced the flow of heat across limbs, suggesting winds that never quite sleep. None of it shouted. Each result refined a picture of climates that follow rules, even when those rules belong to distant weather. Astrometry, once the oldest technique, returned with fresh strength. Subtle motions of stars relative to background fields can carry the imprint of planets on wider orbits. Catalogues grew dense. Systematic errors shrank. Long arcs on the sky curved in ways that made sense when a companion of specific mass and period was added to the model. The method teaches patience, since orbits measured this way unfold over years. Patience has always been part of this subject. Instruments improve. Baselines lengthen. The same star is visited again with better eyes, and what looked like straight motion reveals a slow, beautiful bend. Together these approaches formed a braid of confidence. One measures a wobble, another measures a dip. A third captures a spectrum as thin as a thread, yet rich with meanings. Even microlensing, fleeting by nature, feeds the understanding of how common, distant, cold planets might be. Consistency across techniques is soothing. When different instruments and teams reach the same mass, the same radius, the same orbital period, the object steps out of rumor and into reality with a quiet nod. Names accumulated, and with them patterns. Some systems stacked planets in compact, nearly circular formations with periods linked by simple ratios. Others held one large world farther out, with smaller companions inside, drawing graceful curves. Hot Jupiters remained rare but informative, teaching how migration can reshape youth. Super-Earths proved to be the workhorses, common and varied. Mini-Neptunes showed that envelopes of hydrogen and helium can persist in gentle sunlight. The catalogue does not feel like a crowd. It feels like a garden visited at dawn, each leaf beaded with a small note of light, each note worth pausing over. What began as a suspicion that other stars might host planets became a discipline with standards and routines. The soft footprints are now everywhere, a light curve stored in a database, a velocity time series pinned to a sky coordinate, a spectrum with a shallow notch where a molecule absorbs. The humility of the measurements sustains the subject. Most signals are small. Most detections depend on stability and patience. The result is a body of knowledge that grows like sediment on a lake bed, thin layers building into something solid and wide. The story of discovery rests on a simple posture. Look carefully, wait. Trust the repetition of light. The planets do not need to know they are being watched. They go on with their rounds and allow their presence to be known by the most refined of echoes. A color tilt, a 1% dim, a delay of minutes, an extra glow in infrared. From these quiet signs, entire worlds are confirmed and described. The listener who stands beside the astronomer in imagination can feel how calming this is. Most of the universe remains silent, yet the silence can be read, and reading it becomes a way to sleep well inside the largest room ever known. The expectation began with a tidy picture. A cloud of gas and dust collapses, a star lights in the center, and a flat disk spins around it. Ice forms far from the heat, rock condenses closer in, and the large planets grow beyond the frost line, while small stony worlds collect near the fire. That picture felt complete enough to rest inside. Then a planet the size of Jupiter appeared where only scorched rubble was supposed to live. It circled in a handful of days, kept a tight leash on its star, and turned an entire formation story into a question. The shock did not arrive with thunder. It arrived with a very short orbital period, written in neat figures on a page. Big planets that close to a star stretch theory in several directions at once. Gas should not settle so near to heat that peels molecules apart. Cores should not collect quickly when the disk is still thick with radiation and tides. If such a body assembled far out and later migrated inward, the path had to cross fields of debris without erasing itself in collisions. The surprise served as a lens. Through it, every rule hardened in a classroom softened into something provisional. The sky had written an exception with a calm hand, and the exception was persistent. Another rule gave way when measurements of orbital tilt accumulated. A planet can circle in a plane that does not match the spin of its star. Some even move retrograde, climbing uphill against the rotation of the stellar surface. The Rossiter effect recorded these angles through slight changes in spectral lines during transit. Numbers replaced assumptions. The compact flatness imagined from a single disk gave ground to histories shaped by encounters, tides, and long exchanges of momentum. A system could be orderly without being aligned. That nuance turned a simple map into a living record. Densities pulled the rug again. Worlds of similar size displayed wildly different masses. Two planets with near equal radii might hide very different interiors. One iron-rich and heavy, another cloaked in a broad envelope of gas that makes it light for its size. Mini-Neptunes settled between super-Earths and classic giants, a category without a twin in familiar experience. The catalogue showed a valley in radius distribution near 2 Earth radii, as if some threshold encouraged atmospheres to hold or shed. The lesson was not chaos, it was a deeper order with more pieces than expected. Some planets circle in hours, skimming close enough to pull tails of rock vapor from their faces. The material glows and fades as it streams away, a comet made of a world. Others are puffy, so inflated by heat that their atmospheres balloon past simple models for structure. Even the stability of shape can slip when tides squeeze a planet into an ellipsoid and stir its interior. The quiet shock lies in how often such extremes appear without ending the system. They persist and become part of a new normal that includes outcomes no early sketch allowed. Resonances were supposed to be ornaments. Instead, in some places they shaped the whole melody. Chains where each orbital period links to the next by simple ratios appear again and again. A neighbour's gravity taps a rhythm on another's path, and the paths hold that timing for long stretches. Yet elsewhere, gaps and offsets replace exact locks. Half-captured chains sit beside broken ones. The contrast implies youth full of migrations and near misses, then a long settling into partial order. The original expectation of a single stable layout gives way to a suite of possible architectures, each one a different solution under the same laws. Stellar types complicate the calm assumptions even more. Small red suns can host families of rocky planets that crowd close to warmth, with tidal locking likely for many members. Permanent day and permanent night were once the domain of imagination. They become measurable cases with climate prospects that refuse easy verdicts. Flares from active dwarfs can strip air, yet magnetic fields and dense atmospheres can fight back. The equilibrium is not binary. It lives on a spectrum maintained by competing processes that barely raise their voices. Water used to be placed by simple radius and distance. Then came evidence that some small worlds might be rich in volatiles, with layers of ice or supercritical water deep under haze. Others show signs that their air has been eroded by high-energy light, leaving a rocky core where a mini-Neptune might have stood a few 100 million years earlier. Evaporation sculpted the landscape at planetary scale. The shock here is patient. It speaks in gradual losses and gains that cross thresholds, not in sudden catastrophe. Migration changed from a special plea into a central actor. Interactions with disks can move giants inward like rafts on a slow river. Scattering among siblings can throw one planet outward on a long ellipse while damping another into a close circle. Tides with the star can circularize tight orbits, heating the interior until it relaxes into a new state. Each mechanism has its own timescale and signature. The shared message is simple. The place a planet lives is not necessarily the place it was born. Formation is a prelude. The real composition of a system can be drawn by long drifts and trades that continue for ages. Even the idea of a typical set like the one under a familiar sun turns out to be an outlier rather than a template. Jupiter-sized guardians far beyond the frost line are not the rule. Super-Earths and mini-Neptunes dominate close spans, occupying orbital zones that are empty in the local case. The stress this puts on expectation is oddly calming in the end. It implies variety as the baseline, It dissolves the feeling that one layout should be mirrored everywhere. Atmospheres changed the tune once more by proving readable in detail. Spectra with clear carbon dioxide bands, sodium edges, and water features forced models to include clouds and hazes that mute certain wavelengths and expose others. Superrotation winds carry heat around tidally locked globes, flattening day-night extremes more than simple transport predicted. Some carbon-to-oxygen ratios sit near values that nudge chemistry into unfamiliar pathways. Thermal inversions rise in some regimes and fall in others. The equilibrium structures behave, yet the parameter space is wider than first mapped. Spin and age of stars brought another correction. Stars with rapid rotation and high activity challenge the survival of close envelopes. Older, quieter stars allow thinner air to persist. The same planet around different suns can follow different climate destinies. There is no single habitability line that holds without context. A zone becomes a field of possibilities, shaped by luminosity, history, and spectral color, as much as by distance. Measurement itself added a final, sober twist. Signals that look clean can hide blends. False positives from eclipsing binaries masquerade as planetary transits, and careful verification weeds them out. This constant discipline revealed something larger. The shock is not a single exotic case that disproves a rule. It is a steady accumulation of reliable exceptions that reshape the rule from a sentence into a paragraph. The revised rule still rests on gravity, thermodynamics, and chemistry. It simply accepts a greater range of outcomes as natural. The quiet heart of the shock is humility. The universe followed the same laws that govern stones and steam, yet those laws made patterns nobody sketched in advance. The response has been to widen the frame. Where the old story wanted a narrow path from gas to rock to order, the new story allows many trails that lead to many kinds of order. Orbits can be close or wide, tilts can align or slope, air can thicken or escape. Worlds can keep pace with their stars in constant daylight, or turn with a measured dusk and dawn. The surprise that began with a short period giant near bright light ends as a calm acceptance that the family of planetary systems is broad. The shock never needed spectacle. It needed a few numbers that refused to fit, and then a patient agreement to let those numbers guide the revision. What remains is a set of facts that settles into the mind and smooths it. Planets can be strange while remaining stable. Systems can break old expectations while obeying deeper rules. The vision of order grows larger without losing clarity. It becomes a map that prefers room for new paths, drawn in pencil with a quiet hand. As instruments settled into their tasks, the light from distant suns began to carry layered meanings. Tiny variations in brightness revealed not only the presence of a planet, but the precision of its path, the fineness of its shape, the texture of its air. Time series once treated as simple dips grew into profiles filled with soft details. The ingress of a transit told of limb darkening and planetary radius. The flat bottom recorded the scale of the silhouette. The egress returned light with a signature that could be compared from event to event, and small deviations in timing hinted at unseen neighbors tugging with the weight of months layered upon years. The clock of a star became a quiet ledger where gravity kept its accounts. The ratio of mass to radius took form as a map of possibilities. Each point on that map held an interior story. A dense location suggested iron and stone pressed together until crystal lattices bent. A lighter position implied broad layers of volatile materials, perhaps water in phases that do not exist at everyday pressure, perhaps hydrogen and helium stretched into deep envelopes. The line between super-Earth and mini-Neptune appeared as a valley in the distribution, as if nature preferred to clear a channel between two kinds of planet. That valley spoke of escape, of young worlds shedding air under the push of high-energy photons until an exposed core remained. It also spoke of retention, of slightly larger bodies keeping their shrouds and relaxing into gentle gas-rich lives. Stellar chemistry joined the picture. Metallicities recorded in stellar spectra correlated with the frequency of large planets, while smaller planets appeared across a wider range of stellar compositions. This connection between star and family suggested a calm logic. The material that forms a star also provides the dust and pebbles that seed planets. Enrichment helps build cores quickly, and quick cores gather gas before the disk thins. The result is not fate, only a leaning of the odds, yet even a lean becomes visible when thousands of systems are counted with the same patient method. Thermal phase curves brought the night sides of worlds into view. As a planet orbits, its illuminated face rotates toward and away from the observer, and the combined light changes by a fraction that can be weighed. Those changes revealed hot evenings, cool mornings, and winds that carry heat from a permanent day into a permanent night. Bright spots shifted east of the substellar point in some cases, a sign that air flows with a global coherence, picking up warmth and delivering it to the dark. Albedo estimates emerged from secondary eclipses, when a planet slips behind its star and its own glow is briefly removed. Dark worlds absorbed deeply. Paler ones returned a measurable portion of starlight. These inferences arrived without spectacle, yet each number softened the unknown by a degree. Transmission spectra refined the stories of atmospheres. When starlight passes through the thin shell of a planet's limb, specific wavelengths are absorbed by molecules and particles. Water signatures rose in several cases. Sodium and potassium left narrow imprints. Carbon dioxide drew a clean shape that could be traced across a band. Where signals looked muted, haze and clouds likely scattered light in broad slopes that hid deeper layers. The very presence of haze offered a clue to chemistry and temperature, since small particles condense from mixtures that follow rules. Retrieval models handled the data with care, treating noise honestly, comparing multiple scenarios, and delivering probability distributions rather than single verdicts. The lesson from that restraint was calming. Even with sparse photons, the balance of evidence could be described in a way that honored uncertainty while allowing knowledge to grow. The interiors of tidally influenced planets opened through indirect markers. Love numbers, encoded in subtle changes to transit shapes and orbital precession, hint at how mass is distributed within a body. A planet with a soft interior responds differently to tides than one with a firm core and thin mantle. Measurements of these responses are delicate. They require long baselines and steady instruments. The gains arrive in whispers, a better value for the gravitational harmonics, a tighter bound on rigidity. Each refinement adds a stitch to a tapestry where the patterns are measured rather than imagined. Multiples in compact systems became case studies. When 3 or more planets circle in close order, their mutual pulls trade minutes in transit arrival times. Those trades can be inverted to reveal masses and sometimes eccentricities. The result is a portrait of an entire architecture rather than a single face. In some families, the orbits sit near resonance, guarding one another from close approaches through repeated exchanges. In others, small departures from resonance imply early migrations that settled into near commensurabilities without perfect locks. The difference matters. It tells of paths through a young disk, of slow drifts and nudges that continued until the gas thinned and the music stopped. Obliquity measurements added nuance to the relationship between planets and their suns. During a transit, the passing body blocks different portions of a rotating stellar surface. The resulting line shape changes, track the angle between the orbital plane and stellar spin. Alignments suggest gentle histories. Misalignments point towards scattering, Kozai cycles with distant companions, or disk tilts inherited from birth. The distribution across many stars shows that both quiet and rough pasts leave stable presents. The calm does not erase the memory of earlier restlessness. It simply records that systems can age into balance. Microlensing filled in the cold outskirts. The brief brightening of a background star by a closer one revealed planets many astronomical units from their suns, including bodies with masses similar to Earth. Population studies of these events estimated how frequently cold planets form and survive. The answer was generous. Even far from the central warmth, planets were not scarce. This reinforced a simple comfort. The galaxy produces worlds across a wide range of distances and sizes, and many of them will endure in orbits that change little on human timescales. Directly imaged companions yielded spectra of their own light. Methane features hinted at temperatures. Clouds of silicate or iron appeared in models that fit the data. In some cases, orbital motion was tracked across years, allowing dynamical masses to be measured when combined with parallax and stellar mass estimates. These bright, youthful giants sit far from the frost of their star fields in telescope images. yet their lines and colors contain information about processes that also operate on smaller, cooler planets. Comparing them is like listening to the loudest musician to infer the notes in a quieter part of the orchestra. The longevity of atmospheres under stellar wind pressure became clearer through studies of escape. Ultraviolet light can drive hydrodynamic outflows, lifting hydrogen to heights where it leaves. Heavy elements sometimes hitch a ride in expanding envelopes. During transits, extended exospheres leave signals in specific lines, especially in the ultraviolet. Models estimate mass loss rates and show how a young star's temper can sculpt its inner family. Over time, the flux softens. Planets stabilize into states where escape slows to a crawl. This long view replaces alarm with perspective. The early furnace passes, the later climate persists. A statistical view of habitability emerged without making promises. Planets of 1 to 2 Earth radii in temperate orbits around small stars appeared in sufficient numbers to justify patient follow-up. The term temperate remained careful, defined by incident flux rather than certainty of oceans or rain. Yet even this cautious definition offered solace. With many targets available, a few will align so that starlight filters through air that can be read for water vapor, oxygen family species, or combinations that suggest active cycles. The expectation shifts from whether such cases exist to when the lines will be recorded with enough clarity to draw conclusions. Future observatories sharpened the trajectory. Ground-based giants with adaptive optics promised high resolution and improved contrast. Starshades and advanced coronagraphs defined paths to separate planetary light from stellar glare for smaller, cooler bodies. Time would add depth to baseline, and depth would turn hints into measurements. The cadence of proposals and campaigns continued as a rhythm rather than a chase. Each season brought another slice of phase, another transit, another velocity set that tied mass, radius, atmosphere, and orbit into coherent stories. The calm in these deeper investigations does not come from simple answers. It comes from the way disparate tools point toward compatible pictures. A mass from timing variations matches a mass from radial velocities. A radius from a light curve fits an atmosphere that explains the same light when filtered by wavelength. A thermal map agrees with a wind pattern that also respects the measured obliquity. Consilience grows like frost on a window, thin at first, then spreading in quiet, branching lines until the pane holds a single geometry drawn from countless small crystals. What began as a search for yes or no grew into a practice of listening for quiet structure. The data now hold climates that breathe, interiors that flex, histories written in angles, and futures implied by escape rates. It is enough to close the eyes and imagine the airflow along a planetary limb as it shares heat from day to night, the soft red of a sunset colored by particles, a micron wide, the deep thrum of a magnetic field, shunting charged wind aside. These are not loud images. They are restful for the mind that welcomes patient detail. The universe gives such detail willingly when watched with care, and the result is a knowledge that keeps its voice low. Harmony appears as ratios that feel simple to the ear. 2 orbits complete 3 turns for every 2 of a neighbor. 3 planets trace a cadence where one angle formed from their longitudes hardly changes with time. The mathematics calls these states resonances. The experience of them is a soft lock, a recurring geometry that keeps close worlds safely spaced. Some systems lean into this music, others skirt it, hover near it, or wander away from it entirely. The puzzle lies in why certain families settle into these coherent rhythms, while others drift into spacing that avoids any obvious pattern. Capture into resonance asks for convergent motion. The outer body must gain on the inner one, or the inner body must slow. Young disks of gas provide that slow drift. Torques from the disk handle the migration while the gas also damps eccentricities. When migration is gentle compared with the rate that damping restores roundness, resonance often takes hold. The planets arrive at the commensurate periods, and the resonant angles begin to librate. Their long-term tug-of-war turns orderly, with energy and angular momentum traded in a way that preserves spacing. The resulting chain is more stable than a random arrangement at the same distance from a star. The same recipe can fail when noise enters the medium. Disks are not perfectly smooth. turbulent eddies kick the planets with small, random impulses. If those impulses arrive with enough strength or irregular timing, the capture can be missed. A planet slips past the exact ratio by a hair, the angle fails to lock, and the neighbors move on. Later, they may sit slightly wide of resonance, close enough to feel its pull, not close enough to live inside it. This near state leaves a fingerprint in period ratios that cluster just above simple fractions. The sign is quiet but persistent in the statistics. Even successful chains can loosen. Once the gas clears, tides inside planets and within stars begin to work on orbits that sit very close. Tides prefer to damp eccentricity. In a resonant system, damping of one body forces energy into the others, widening the period ratios. The configuration remains related to a resonance, yet shifts outward in small steps, a process sometimes called resonant repulsion. The chain still remembers its past. The synchrony remains clear in timing variations and in low mutual inclinations. The music slows rather than breaking. Spacings carry another measure of calm. The separation between orbits in units of mutual Hill radii predicts whether the configuration survives for long. When neighbors lie within a few mutual Hill radii, gravity can push them into encounters on timescales short compared with stellar ages. Wider spacing raises the threshold for chaos. Many compact sets live near the boundary where resonant protection matters most. The lock prevents close approaches that would otherwise occur. Where spacing already sits comfortably wide, resonance becomes a possibility rather than a necessity. Such families can ignore the rhythm and still enjoy long quiet. Angular momentum deficit offers a complementary view. This quantity sums how far a system sits from perfectly circular and coplanar motion. Low deficit implies a wide region of phase space where orbits behave quasi-periodically, a landscape the KAM theorem sketches with surviving tori. High deficit squeezes those islands of predictable motion until they touch and break. In that regime, small differences in initial conditions lead to wandering longitudes and slowly growing eccentricities. Collisions or ejections may wait far in the future, yet the grace has left the dance. The distribution of deficit across known systems hints that the calm ones simply carry less dynamical heat. Secular interactions can preserve or spoil peace depending on geometry. These interactions do not depend on the exact positions of planets but on averaged pulls over many orbits. They trade eccentricity and inclination in cycles that repeat on long periods. If the frequencies of these trades align with the natural frequencies of the orbits, a secular resonance occurs. In some architectures, this resonance pumps eccentricity until orbits begin to cross. In others, the resonance keeps values low through delicate phasing. The outcome depends on masses, distances, and inclinations in a way that allows both quiet and unrest under the same laws. Inclination plays a role often overlooked. A set may appear non-resonant in the line of sight because only one member transits. The unseen neighbors could still participate in a resonant chain tilted by a few degrees. Conversely, measured misalignment between planetary planes can weaken resonant coupling. The angles that would otherwise librate lose their coherence when nodal longitudes precess at mismatched rates. A gentle tilt can thus act as a slow detuner, nudging a once harmonic set into a near state that looks similar but carries less protection. Mass ratios color the portrait. Equal mass neighbors exchange momentum efficiently and are more easily locked during migration. Large contrasts pass through resonance with less friction, making capture less likely. The surface density profile of the disk sets the usual mass hierarchy among forming worlds. In regions where pebbles and planetesimals supply similar growth rates, planets may arrive with comparable masses and sing together. Where one body steals material early and grows dominant, the chorus becomes a solo with distant accompaniment, and resonance recedes. Edges in the disk provide stage marks. Pressure bumps near snowlines or magnetospheric truncation points slow migration and can trap planets. Chains built at these traps inherit a resilience because the last step of convergent motion occurs in a region with gentle gradients. If the trap later dissolves or moves, the chain may drift intact. Without such anchoring, the same bodies might have scattered or missed capture. The presence or absence of traps in a given birth environment therefore changes the odds of harmony in a way that leaves no direct trace once the gas has gone. After the gas era, a swarm of leftovers continues to interact. Planetesimals deliver small kicks that accumulate. In some models, this late rain nudges planets just far enough to break locks. In others, the cumulative effect remains below the threshold and the locks survive. The final outcome is statistical, not deterministic. Two systems with nearly identical birth conditions can diverge because of the particular draw from a vast deck of small bodies. The calm that follows has the feel of a coin landing on a cloth. The sound is soft, the result definite, the cause distributed over many tiny taps. Tidal dissipation inside planets plays its own quiet tune. Rocky bodies and mini-Neptunes convert periodic stretching into heat with different efficiencies. When the dissipation is strong, resonant forcing on eccentricity is damped more quickly. The damping widens period ratios and reduces the amplitude of any libration. When dissipation is weak, the lock holds with small oscillations that can endure for as long as the star remains steady. Two similar sets can thus part ways because of differences in composition and interior temperature, hidden factors that only reveal themselves through a slight offset from an exact ratio. Magnetic activity of the star adds a small, indirect influence. Strong winds and flares shape escape from close atmospheres, adjusting mass over time. A change in mass shifts the gravity budget that controls resonant angles. The effect is subtle, yet across billions of years, subtle accumulations matter. A chain that appears perfect at youth may drift toward imperfection at age, not through sudden shock but through the quiet bookkeeping of stellar weather. Observation tends to favor the tidy. Resonant sets with multiple transits are easier to confirm and study. Non-resonant families with higher inclinations can masquerade as sparse. This selection shapes impressions. When corrections are applied, the picture still shows a meaningful mixture. True chains exist, near chains abound. Wide spacings without simple ratios remain common. The harmony problem survives as a live question rather than a solved exercise. Calm has many sources within this puzzle. Convergent migration can lock, disk traps can assist, modest mass ratios can help, low angular momentum deficit can shelter orbits in regions of predictable motion. Tidal damping can ease systems away from violent corners of parameter space. Even when resonance fails or fades, enough spacing can protect. Stability is not a single mechanism, it is a fabric woven from several threads, each strong enough to carry part of the load. The opposite fate has its own dignity. A family that never found a lock can still live long if its members keep their distance. Even a chain that once existed can dissolve and leave a layout that looks unremarkable yet persists. Cascades of collisions and ejections do occur, but they are only one end of a spectrum that mostly settles into survivable order. The rarity of recent catastrophes is itself a calming fact. Most skies keep their patterns, even if those patterns refuse to be counted in small integers. The harmony problem thus becomes a meditation on tolerance. Nature permits many ways to be quiet. Resonance is one, generous spacing is another. Low eccentricity achieved through damping is a third. Mixtures exist, along with transient states that last longer than any audience. The ratios written by a few systems become emblematic, yet they are only a sample from a gallery of stable geometries. The music of orbits can be obvious or hidden, strict or relaxed, loud in angles that lock or soft in amplitudes that never grow. What unites them is endurance set by gravity, time, and a world's willingness to yield a little when pulled. Gravity teaches water to breathe. It presses and lifts with a rhythm set by the geometry of two bodies crossing their invisible lines. On a world that keeps an ocean, the pull of a nearby companion draws tides that glide around basins like long-traveling sighs. On a dry world with a molten interior, the same pull kneads rock into warmth and slows the spin into a gentler tempo. The grand result is a patient correction. Excess motion drains into heat, wild angles settle, rotations drift towards simple states. What begins as restless energy becomes climate that behaves. Tidal locking is the most familiar outcome. A planet that orbits close to its star feels a persistent bulge along the star line. If the surface rotates faster than the orbit, the bulge lags. Friction in rock and ocean works on that misalignment, pulling back against the spin. Over millions or billions of turns, the the rotation slows until one hemisphere faces the star with steady loyalty, while the other keeps a permanent night. The process is not violent. It is incremental, a rearrangement of angular momentum by tiny torques spread over epochs. At the end sits a quiet geometry that refuses surprises. Sunrise and sunset occur only at the edges of a great circle, where day fades into night with no hurry. The factor that sets the pace for this drift is often written as a quality called Q. A lower Q means the body wastes rotational energy more efficiently as heat during each stretch and release. A higher Q allows the world to flex and relax with little loss. Rocks with partial melt, oceans that slosh across wide shelves, and atmospheres that carry pressure waves all lower Q. Icy mantles with friction between layers do so as well. The number is not a fixed property. It changes with temperature and composition, so a world can speed or slow its march toward locking as it warms or cools. The feedback is subtle and soothing. Dissipation warms the interior, warming changes Q. The new Q changes the rate of dissipation again, finding a balance that picks a timescale suited to the planet's materials. Many close planets do not arrive at exact synchronous rotation. Eccentric orbits produce a wobble in stellar distance. The moving torque can trap a body in an integer ratio such as 3 spins for every 2 orbits. Mercury follows that path around its Sunday capture into such resonances depends on how triaxial the body is, on Q, and on the rate of orbital circularization. The structure that results is still regular. Sunlight rises and sets, yet with a cadence that repeats exactly, painting the landscape with predictable cycles of heating and cooling. For climate, the outcome remains gentle compared with chaotic tumbling. Once a lock is established, climates respond with patterns that calm extremes. On a synchronous world, the substellar point receives continuous light. Air heats, rises, and flows outward at high altitude toward the permanent night. At the antistellar point, the same air cools, sinks, and returns as a surface wind. This cell creates a conveyor that transports heat efficiently. If the atmosphere is dense enough, the day side does not scorch, and the night side does not freeze to airless silence. The twilight belt around the terminator can settle into temperatures where liquids can last, and clouds can patrol familiar tracks. Even without oceans, this ring can host a persistent, dim afternoon that hardly shifts from one year to the next. If seas exist, they widen the calming effect. Water stores heat and returns it slowly. Ocean currents, driven by winds and planet rotation, carry warmth into the dark and return cool water to the light. The thermal inertia smooths daily and seasonal cycles until weather moves with a languid pulse. Waves break with similar heights from week to week. Storms may form along predictable lines and then unwind with reliable decay. The sound the climate makes becomes a hum rather than a shout. Creatures that might evolve under such a sky would learn rhythms that rarely betray them. Tidal heating supplies another layer of moderation when orbits retain some eccentricity. As a planet travels from periastron to apastron, the tidal bulge expands and contracts. Internal friction converts that flexing into heat. The distribution of heat depends on the interior structure. In rocky bodies, it warms the mantle and can sustain partial melt far longer than radiogenic decay alone could manage. In icy bodies, it can maintain oceans beneath crusts. For climates near the edge of cold stability, this steady extra warmth can prevent a global freeze. A planet that would otherwise slip into a white mirror can hold on to a dark patch of open water at the substellar point, and that patch can power a local hydrologic cycle that resists collapse. Obliquity responds to tides with a tendency to fall. A large tilt makes seasons that swing between extremes. Tidal torques act to align the spin axis with the orbit normal, damping the angle over long spans. A small residual tilt means seasons that barely whisper. The sun migrates a few degrees north and south across the sky, and the difference between solstice and equinox becomes a modest shift in wind position rather than a change in the character of the year. When combined with heat transport in air and water, this small obliquity lets landscapes keep their temper without lengthy winters or short, violent summers. Eccentricity diminishes as well. Planetary tides and stellar tides exchange energy and angular momentum until the orbit rounds. A circle removes the greatest thermal swing, periastron no longer brings a hot pulse. Apastron no longer brings a cold lull. The insulation becomes a constant surface over time. On a synchronous world, this rounding converts the heating pattern into an almost static map anchored to position rather than season. Clouds gather near the updraft where sunlight is constant. Precipitation rings form at predictable distances. Outside those rings lie deserts of gentle quiet, where wind draws dust in arcs that repeat for generations. Magnetism feels the tides indirectly. If tidal heating maintains a slow simmer in a liquid core, convection can continue and a dynamo can persist. A magnetic field then shields the upper air from stellar wind, lowering escape rates for lighter gases. The protection supports the broader calming effect by keeping pressure high and maintaining greenhouse layers. With enough time under guard, even a close world can keep a stable atmosphere that remembers its own past rather than losing itself to space. There is a limit to softness. Excessive tidal heating can drive volcanism that fills the sky with haze and throws climates into cycles of warming and dimming. Yet the same mechanics carry a path out of excess. As eccentricity damps, the heating budget declines. Systems move from wild youth into a middle age where resurfacing slows, geysers calm, and haze thins to a manageable veil. The narrative bends toward regularity, unless a companion maintains the eccentricity with resonant tugs. In multi-planet families, delicate balances arise where one neighbor provides just enough push to sustain mild heating without triggering collapse. The outcome is a steady simmer that neither starves nor burns. Atmospheres themselves carry thermal tides that talk back to gravity. The daily heating on a dayside drives pressure waves that circle the globe. Where these waves lead or lag the substellar point, they exert torques on the surface below. If strong enough, they can settle the rotation into a rate slightly faster than synchronous, a condition sometimes called asynchronous equilibrium. This state produces a slow progression of the terminator that draws the climate map in drifting light. The movement is small, the period long, but the effect can distribute rainfall and prevent permanent cold traps from swallowing the night side. It is a quiet compromise between a locked world and a freely spinning globe. Coasts form with the help of tides. Repeated rise and fall sets erosion patterns and builds deltas that grow with dependable rhythm. Salt marshes breathe in and out. Estuaries circulate nutrients along predictable paths. Even in alien chemistry, any liquid that collects will discover similar dynamics under periodic pull. The landscape learns to accept the motion and shape itself around it. Over geological durations, the resulting geography favors moderation. Broad shelves, damp waves. Rounded estuaries buffer storms. Barrier ridges reform after each slow bite of the sea. Land and water settle into a conversation that repeats. The comfort in tides lies in their patience. They do not demand attention. They do not seize a world by surprise. At each orbit, they move a small amount of energy from motion into heat and from misalignment into alignment. They lay down cycles in rotation, in sea height, in air pressure, in tectonic release. They smooth the sharp edges that youth creates and lay out the reliable gradients that life and weather can use. Worlds that start with too much spin learn to match their companions. Worlds that start with wild seasons learn to reduce them. Worlds that fear permanent day or night find that fluids and winds can knit the halves into a functional whole. There is a picture worth holding. A globe with one face lit, the other in shadow, wrapped in an atmosphere just thick enough to carry warmth. At the rim where light meets dark, a perpetual evening runs around the planet. The sea there rises and falls by quiet centimeters. The breeze drifts outward near the surface and returns aloft in a slow river. Clouds form in wreaths and slide across a sky that keeps the same star in place. Far overhead, the boundary between space and air glows faintly where particles meet the magnetic field and turn aside. Somewhere below, rock flexes by fractions of a millimeter with each orbit, and the flex keeps a deep heat alive. The scene does not change quickly. It improves its own balance with each passing year. Tides are often thought of as forces that drag. In truth, they are teachers that coach worlds toward composure. They reduce violence in the long run by spending the currency of motion. They assign climates a cadence. They make geography a participant in atmospheric rhythm. They keep oceans awake when they might sleep under ice, and keep winds round when they might shatter into jets. In the slow arithmetic of planetary time, such teaching adds up to serenity, and serenity is the most calming fact to carry into sleep, that worlds learn to rest. An atmosphere holds a planet the way a weighted blanket holds a resting body. It does not pin, it steadies. Molecules crowd together in a shell that thickens downward, each layer pressing the one beneath, until air becomes a slow-moving reservoir of heat. The reservoir takes in warmth during the bright hours and yields it back after night arrives. In doing so, it smooths the rhythm of temperature from spike and drop into curve and glide. Even a modest column of gas can soften the harshness of sunlight and the emptiness of darkness. A deep column does more. It makes weather that remembers. Composition decides which wavelengths of light are welcomed and which are stored. Nitrogen and oxygen do little work except carry heat and mass. It is the trace gases, the carbon dioxide, the water vapor, the methane, and on some worlds the hydrogen and helium themselves that set the radiative script. Photons from a star enter primarily invisible light, meet clouds that scatter or surfaces that reflect, and then leave as infrared that is absorbed by vibrational modes of molecules. Pressure-broadened lines overlap until the air glows inward as much as outward. The result is a greenhouse that does not so much trap heat as delay its departure, holding the warmth long enough for night to receive its share. Mass strengthens the effect. With more air above each square meter of ground, convection has more material to push. A rising parcel loses heat to expansion, but stays warm longer when the lapse rate is gentle. The dry adiabatic gradient, set by gravity and specific heat, establishes a baseline. Add water or other condensables, and the gradient softens further because latent heat is released as vapor turns to cloud. Skies with generous humidity build a troposphere, where temperature falls slowly with height, a morphed staircase rather than a steep descent. That softness is felt at the surface as mild days and forgiving nights. Hydrogen-rich atmospheres bring their own calming power. Collision-induced absorption, a dance where two molecules briefly act as one radiator, gives even symmetric molecules a way to hold infrared light. At pressures of tens to hundreds of bars, these absorptions blanket worlds with warmth out to large distances from their stars. A small planet wrapped in enough hydrogen can keep oceans that would otherwise freeze. The blanket is not fragile. Collisions are common in deep air, and the heat pathway remains open across broad bands. The pipe organ of the spectrum plays fewer sharp notes and more low hums that carry through the long night. Clouds serve as caretakers that adjust in real time. When surface heating intensifies, convection lifts moisture until droplets and crystals form, an increase in albedo that reflects extra sunlight. When heating weakens, clouds thin and the ground sees more of the star. The feedback is not perfect, yet it guides climates toward temperance. Different chemistries produce different collectors of light. Water clouds scatter visible wavelengths with bright efficiency. Methane clouds in cold air, sulfuric acid droplets over hotter layers, silicate and iron grains in giant planet skies. Each has its preferred temperature and altitude. Together they work as an adaptive mirror that reduces the range of seasons and hours into something a landscape can rely on. Winds enroll in the task. On slowly rotating planets, the pressure gradient between warm and cold sides organizes a global cell with an upwelling under perpetual day and a downwelling under perpetual night. On faster rotators, the Coriolis effect divides the flow into bands and gyres, yet even then the bulk of the circulation transports heat poleward and nightward. Superrotation often appears a jet around the equator that carries air east faster than the surface. The jet spreads dayside warmth and lowers the contrast that would otherwise stress rock and ice. The map of temperature becomes more a broad smear than a checkerboard. Scale height is another quiet comfort. Thicker air means a larger scale height, the distance over which pressure falls by a factor of E. With larger scale height, mountains bury their peaks in air that still holds heat, and valleys do not pool cold as deeply. Topography loses some of its leverage over weather. Downslope winds still form, but their chill softens. Rain shadows persist, but their dryness blunts. The atmosphere becomes a unifier of diverse terrains, rather than a tool that sharpens the line between them. Dust can act as a soft dimmer when kept in modest amounts. Particles lofted by breezes absorb and scatter sunlight, warming the air slightly and shading the ground. If feedbacks hold the concentration near a stable point, the haze reduces extremes without choking the sky. The balance depends on sediment availability, uplift, and precipitation that washes the column clean. On worlds where liquid is scarce, long-lived hazes may linger for seasons, coloring sunsets and lowering the daily swing. On worlds with abundant rain, dust pulses come and go like quiet phrases in a longer song. Photochemistry writes rules about who lives where in the air. Ultraviolet photons slice molecules, and the fragments recombine into new species, some of which form aerosols that shade, others that absorb at specific windows. An atmosphere already rich in nitrogen and methane might build complex organic haze that softens the spectrum and cools the surface slightly, while also retaining heat in the middle layers. The vertical profile becomes a set of layers that trade light among themselves until the ground feels a moderated result. The chemistry listens to the star's color and to the magnetic protection above. Under calmer stars, the stratification settles into routines that last. Surface pressure directly controls the diurnal range. A thin air allows ground to heat quickly under sun and cool quickly after dusk. A thick air damps both. Specific heat of the gas is the measure, how much energy a given mass can store per degree. Hydrogen and nitrogen carry large capacities. Carbon dioxide slightly less, water vapor more through its latent storehouse. Put together, these properties define the inertia of the climate engine. High inertia smooths noise and accepts perturbations without lurching. Changes in insulation from modest eccentricities or slow variations in stellar output are buffered into shifts that take centuries rather than years. Oceans and atmospheres in partnership perform even better. Evaporation cools the surface, condensation releases heat aloft, rainfall returns mass to sea that then redistributes energy through currents. The interface blurs the line between water climate and air climate into one system that resists abrupt flips. On worlds without oceans, thick air can still provide comparable memory. Ground warms the surface layers, those layers share laterally, and the night pays back the heat with interest. The swing is gentle, and the pattern repeats. Storms remain, yet their edges soften under weight of air. Strong vertical shear and sharp contrasts feed the fiercest weather. A heavy blanket diminishes the fuel, updrafts spread wider, gust fronts weaken, and precipitation falls as long, steady rains rather than violent squalls. Sounders at infrared wavelengths would view these scenes as broad cold tops and gentle anvils rather than spikes of convection. Lightning can still lace the clouds, but the intervals lengthen and the footprints spread. The narrative of a season reads as continuity, not as punctuated alarm. A calming detail hides in the mathematics of radiative timescale. The time a layer of air needs to heat or cool by radiation scales with pressure and heat capacity. Double the pressure and the timescale lengthens. Double the heat capacity and it lengthens again. When that timescale exceeds the length of a day, the concept of day and night loses sharpness for the air. Heat redistributed by winds has time to act before radiation can reimpose the pattern of the star. This simple ratio is a quiet arbiter of comfort. Thick air gives weather a long memory, and long memory breeds moderation. Magnetic fields keep the top of the blanket from fraying. Charged particles from a star would otherwise hit the upper air, break molecules, and drive escape. A field diverts much of the wind. Even without a robust magnetosphere, high mass alone anchors the lowest layers, helping them survive the gradual loss of the very lightest species. The blanket may thin a little with age, yet in many cases it remains present enough to do its work long after youth has passed. No single pressure or recipe guarantees calm. Too much greenhouse input and the surface warms beyond gentle bounds. Too much aerosol and the light starves. Yet most combinations produce regimes where living at the surface would feel predictable hour by hour. Skies build habits. Wind maps repeat. Cloud belts patrol familiar latitudes. The eye could learn the weather, the way it learns the face of a friend, by the constancy of small variations. Picture a planet with a generous sky, a light that filters through high veils, and a ground that warms by degrees and then rests. There is no harsh noon, only a wide plateau of afternoon. There is no sudden night, only a slow bluing toward darkness. Far above, molecules absorb and emit like countless tiny hearths. The column hums with steady exchange. Beneath it, quiet rivers carry reflections past stones that have forgotten sharp corners. The air is the architect of this patience. It is the assurance that tomorrow will resemble today, that a world can carry softness as a permanent feature, that rest is built into the physics of gas and light. Small stars live at a slow tempo. Their fires burn in deep red, their pulses run long, and their promises extend far beyond the lifetimes of brighter suns. In that soft light, planets can circle for spans that make continents look young. The physics is straightforward. With less mass, fusion proceeds at a measured rate, and the core mixes fresh fuel into the flame. A modest star that stirs itself so thoroughly spends everything carefully. The result is an era that can last into trillions of years, a stretch of time generous enough for climates to practice patience and for landscapes to perfect balance. The glow favored by such stars leans toward infrared. Planets close enough to feel warm receive light that penetrates clouds and air in different proportions than the blue rich beams of larger suns. This color matters. Water vapor absorbs readily in bands peppered across the infrared, and surfaces reply by releasing heat in windows that the air still grants as pathways to space. The exchange writes smoother curves into daily temperature tracks. Under an old, quiet red star, the diurnal story is about moderation more than contest. Habitability resides near the hearth. The temperate band lies close, with orbital periods counted in days or weeks. Proximity brings tidal effects that tend to slow rotation until one face lingers in daylight and the other rests under a permanent night. That geometry sounds stark until air is allowed to move. Winds loft warmth outward from the lit center, then deliver it back along the ground after chilling above the dark hemisphere. With enough pressure, the loop becomes efficient, and the world evens itself out. Along the twilight ring, the sky holds a perpetual evening, a long gradient where rivers of cloud pass with regularity. For a planet that wears a substantial atmosphere, this arrangement steadies life at the surface instead of threatening it. Young red dwarfs speak in flares and bursts. Their magnetic fields twist, store energy, and let it go as bright spikes of ultraviolet and X-rays. The behavior is common early, when spins are fast and fields are strong. With age, rotation slows and activity declines. Decades of monitoring show that late in life, many of these stars fall into calm habits. The flares still occur, yet the intervals lengthen, and the peaks lower. Farther benefit comes from periods of quiet that last long enough to let atmospheres repair the work of chemistry above the clouds. Ozone layers can rebuild, and aerosols can settle from the middle air back toward the surface. Patience returns after youth has spent itself. Pre-main sequence phases complicate the picture with a warm prologue. Before full stability, the luminosity runs higher at the same mass, leaving the close orbits bathed in more light than they will later see. Oceans laid down too early may evaporate, and hydrogen may escape. Yet even this hazard admits avenues of ease. If deep mantles retain water and release it slowly, seas can form late. If initial inventories are large, they can survive a youthful bake and arrive in middle age with quiet depths. The difference is not exotic. It is a bookkeeping of volatiles, a matter of reservoir size and release schedule. Over the grand span, a modest star offers so much time that late comfort remains plausible. Magnetism on the planetary side enters as a shield rather than a sword. Close orbits feel wind. A magnetic field gives charged particles a longer road to the ground, bending their paths and spreading their energy across wide auroral ovals instead of letting them strike directly into the upper air. The protective value rises when rotation remains energetic enough to sustain a dynamo in a liquid core, or when internal heating keeps convection active even in slow spin. With a field in place, the top of the atmosphere can keep its chemistry intact, and the lowest layers hold their pressure for eras that outlast mountains. Clouds under red light have a special role at the point of endless day. Bright, Persistent convection above the substellar region seeds a ceiling of droplets that reflect a portion of the incoming glow. That reflective cap reduces heat input where it would otherwise be most intense. The effect is a break that can hold a climate below runaway, even when the star sits nearby. Away from the central column, thinner veils pass light and let the surface warm enough to continue the engine of circulation. The pattern is self-managing. Increased heating thickens the canopy, which then lowers the heating again. Decreased heating thins the canopy and lets more in. A stable cloud thermostat emerges without a designer. The color of light affects potential photosynthesis. Photopigments tuned to red and near-infrared can harvest energy from a star that gives little in blue. The physiology would differ from that of green leaves, yet the principle remains the same. A photon caught, an electron raised, a chain of transfers that stores energy in bonds that feed metabolism. The surfaces that support such chemistry would look dusky at noon and glow in long sunset hues even at midday. From orbit, a spectrometer might see vegetation edges displaced toward longer wavelengths, a gentle signature of local adaptation to a gentle star. Seasons quiet down as well. Small stars exert limited tugs on distant companions that might otherwise tilt the inner world or pump its eccentricity. Without strong perturbers, the angle between spin and orbit can rest near small values, and the shape of the path can round toward a circle. The star itself is compact and stable, so changes in luminosity creep slowly. The resulting year carries modest transitions. Rain belts migrate by degrees. The thermal equator walks by a few steps. The maps that farmers would consult in imagination look much the same from generation to generation. If moons form or are captured in such settings, tides develop routines instead of drama. Periodic rise and fall cuts shallow channels, builds marshes that breathe, and seeds estuaries with predictable mixing. On a locked world, the dominant rhythm may come from libration in sunlight or from the small variations in distance during slightly eccentric motion. The energy delivered arrives on time, and ecosystems would learn to open and close in sync with it. In the long calm of a red dwarf epoch, such partnerships could refine themselves with an artistry that only patience allows. The architecture of multi-planet families around small stars often shows close spacing and low-mass members. Their mutual pulls settle into near-resonant relationships, and their inclinations remain slight. The compactness keeps the stable region small but well protected. It also places several potential temperate surfaces under the same star, each with a different balance of air, water, and rock. Diversity occurs within the same gentle light, a gallery of climates that repeat their cycles with similar beats. For observers, this offers comparative cases that teach the rules of moderation more clearly than any single world could. Chemistry above these planets reads the softer spectrum and tends towards slower photolysis of key molecules. With limited ultraviolet flux, methane can persist longer, and oxygen produced by non-biological means accumulates less readily unless water is relentlessly split and hydrogen lost. This spectral balance reduces some of the confusing signals that would otherwise masquerade as signs of life. It also encourages the growth of hazes that shade without suffocating. The layers stack into a structured sky where radiative cooling and warming oppose in a near tie. The ground below then sees a steady climate with few abrupt reversals. Quiet red dwarfs still carry spots that turn light into a slow modulation as the star spins. The roll changes the brightness by small percentages over weeks. Planets adjust by continuing the same circulation patterns with slightly shifted strengths. No singular event forces a new regime. A listener to the climate would hear a long, low beat with faint harmonics, nothing like the sudden drums that large flares once provided in youth. Where the star runs a magnetic cycle, the amplitude of spots waxes and wanes gently, and the planet replies by adjusting cloud cover in proportion. The most restful fact remains the calendar written by such stars. With lifetimes that dwarf those of larger suns, they make room for long experiments in stability. A world that finds an equilibrium at a few 100 million years could hold it for spans 1,000 times longer. Continents could rearrange in slow ballet without the sun changing its mind. Oceans could settle into currents that define coasts for ages. Biochemistry could try variations without fear that the stage will collapse. The universe seldom grants guarantees, yet in the company of these small fires, it offers conditions that approach them. To picture the peace of a red dwarf system is to picture a sky with a steady ember at its center, a tide of warmth that never rushes, a wind that keeps to its lanes, and a clock that ticks without hurry. Flares happened when the star was quick, then faded as the star slowed. Atmospheres learned to heal faster than they were harmed. Magnetic cloaks learned to bend gusts without tearing. Oceans, if present, learned to trade heat across a planet that welcomed a constant evening around its waist. The sum is not silence, it is a confident murmur. Under that murmur, a planet can rest, and a mind can follow it there. Magnetism curls around a planet like an unseen cloak. Deep within, a liquid core turns, and that turning organizes electric currents that write lines of force into space. Charged particles from the star feel those lines and slide along them rather than plunge straight into the air. The field does not stop the wind completely, it redirects and dilutes it, spreading energy over wide auroral ovals and surrendering only a fraction to the upper atmosphere. The protective effect is quiet but profound. Molecules that would have been broken remain whole. Light atoms that would have fled remain part of the sky. The surface inherits a calmer climate because the topmost layers stay thick enough to do their work. A moon can contribute without shining. Its pull needs the planet and keeps convection alive in the core, preventing the stratification that would smother a dynamo. The same rhythmic flexing helps maintain a gentle heat through the mantle, sustaining volcanism modestly rather than catastrophically. With heat moving and metal flowing, the field persists. The rhythm is measured in days and months, yet its gift is measured in million-year stability. A world that might have cooled into magnetic silence continues to hum. Obliquity benefits as well. A large satellite exerts a steady torque on the equatorial bulge of its planet. That torque resists the random leaning that distant companions and stellar tides would otherwise cause. A stable tilt keeps seasons within narrow bounds. Summer arrives by degrees. Winter retreats without drama. The path of storm tracks wanders by small latitudes rather than by continents. In the geometry of climate, a moon is a hand on the shoulder that keeps the dancer balanced. Where a giant planet holds many moons, resonance can maintain small eccentricities and produce steady internal heating for the satellites themselves. 2 or 3 bodies locked in simple ratios exchange angular momentum with a regularity that preserves deviation from perfect circles. The heat created by this deviation melts ice under crusts, the way a soft kettle keeps water steaming without a boil. Subsurface oceans become enduring features rather than passing episodes. Their roofs protect them from radiation, while the giant's magnetosphere often shelters the system as a whole from much of the stellar wind. In such a setting, the nights above become gentle. The harmful particles that would spark through a thin air instead ride the field lines and spill their light mostly at the poles. Radiation belts do form within magnetospheres, yet even here the presence of moons can soften conditions. Orbital paths sweep through the belts and scatter or absorb trapped particles, carving partial gaps and lowering intensities in specific regions. Volcanically active moons feed the system with neutral gas that becomes ions, but that same material can redistribute charge in ways that regulate the belts. The overall result is not a simple reduction of energy. It is a quieting of sudden spikes and a pattern that a landscape can learn. Moons do more at the surface level. Tides they raise in seas and atmospheres organize cycles of mixing that deliver nutrients and maintain oxygen in coastal waters. The precise height and timing depend on distance and geometry, yet the predictability is the key. Ebb and flood teach estuaries to breathe. Sediments rise and settle on schedules that build marshes and deltas. Even on worlds without abundant water, atmospheric tides push and pull on the lowest layers and nudge circulation toward repeatable patterns. Clocks do not need to be invented when the sky itself provides them. Night becomes a design project shaped by magnetism. At high latitudes, charged particles guided by field lines collide with thin air and paint auroras that sway slowly. On a tidally locked world, the night side sees a persistent pattern as plasma flows adjust to the fixed substellar point. Curtains of light gather near the magnetic cusps, rise in dim waves, and fall again. Between those ovals, darkness can be remarkably clean. Cosmic rays arrive in fewer numbers after the magnetosphere sifts them. High-energy photons from the star are absorbed in the upper layers that remain intact. The quiet is literal. Air glows faintly. Stars in the sky hold steady. If the planet lives near a red star and carries a field, another kind of calm emerges. The stellar wind may be dense, but the magnetopause bulges outward and deflects it. Reconnection events still occur along the boundary, yet their energy pulses as regular weather rather than sudden catastrophe. The field lines stretch into a tail that shelters the nightside from direct flow. Eclipses by a moon bring predictable drops in light that mark hours for creatures and cycles for plants. Planetshine returns a gentle glow to the moon, making twilight that lasts through another rotation. Detection of these magnetic worlds often uses radio whispers that leak from the poles. Electrons spiral and emit at characteristic frequencies set by the local field strength. The sound in instruments is a hiss that rises and falls with orbital phase. To listeners on the ground, the radio noise would not intrude. It is a sign at a distance, a tracer, that reveals the existence of a shield working as intended. The presence of such emissions implies a certain level of interior motion and a certain resilience against atmospheric loss. It is a comforting inference that links unseen deep currents to the hush felt at the surface. Exomoons themselves can host gentle climates when they circle within the broad temperate zone of a star and share a giant planet's protection. They receive light from the star, light reflected from the host planet, and heat from their own tidal work. Eclipses slide across their faces with a cadence that can set internal clocks. The planet looms as a constant disk, providing a fixed point in the sky that anchors long perspectives. Radiation from the belts may brighten the poles with quiet aurora, yet the thick air below blunts the dose. The nights on such moons would glow with steady colors, and the days would pass with patience. Ring systems contribute by screening micrometeoroids and distributing dust that settles slowly. A ring can act like a wide, thin shield that takes small impacts through countless particles and reduces the flux of debris that reaches inner environments. The dust that escapes the ring drifts into the magnetosphere and becomes part of the plasma that shapes auroral forms. The process is diffuse and ongoing, a background maintenance that keeps catastrophic strikes rare and blunts their effects. In some geometries, induced magnetism appears. A saltwater ocean under an icy shell conducts, and the changing magnetic field of the host planet drives currents that create secondary fields. These induced fields partially cancel the changing external influence and reduce energy deposition in the interior. The same induction reveals the ocean to remote observers, since the magnetic signature varies with orbital phase. The ocean thus helps protect itself simply by existing, another self-reinforcing loop that favors endurance. Moons also serve as gravitational companions that damp the long-period wobbles of a planet's rotation. Without such damping, small shifts in precession could resonate with secular cycles and swing the climate between extremes. With the companion present, the precessional frequency moves off those dangerous alignments. The atmosphere then sees slow cycles that never cross the thresholds for runaway ice or runaway greenhouse. Snow lines migrate, forests or their analogues adapt, yet the underlying pattern never quite loses its balance. A quiet night is not empty. It is filled with backgrounds that stay within known bounds. The magnetosphere hums, the aurora shifts a little, the tide rises and falls along coasts or under ice. The wind follows familiar paths from pressure highs to lows. Occasionally, a flare from the star ruffles the top of the shield. The response is a bloom of light at the poles, a temporary expansion of the auroral oval, and then a return to form the atmosphere below scarcely notices. The stability comes from layering, field above, light below, mass in between, and cycles that stitch them together. When several planets share a system and each carries a field, their interactions produce additional rhythms. Magnetic connections can form briefly as orbits bring magnetospheres close. The events are gentle meetings in vacuum, transfers of charged particles and adjustments of current sheets. For any single world, the effect is a slight alteration in auroral brightness and a modest tweak to the high-altitude energy budget. These variations write slow beats into the sky rather than shocks. Over time, they become another element in the familiar score that life and weather play by. The most calming truth is that such protections do not require perfection. A field can be modest and still valuable. A moon can be small and still steady a tilt. A ring can be thin and still share the burden of impacts. The result is a network of supports that turn a potentially harsh, stellar neighborhood into a place where nights are safe and days are predictable. The physics is straightforward, but the combined effect is art. Magnetism draws the frame, gravity paints the motions within it. From that collaboration arises the quiet night that invites sleep. A planet begins long before it has a name. It begins where dust meets frost and chemistry turns a corner. In a young disk around a newborn star, temperature falls with distance, and that gradient paints invisible rings called snow lines. Each ring marks the place where a vapor condenses into ice on grains. Closest to the fire, metals and rocks survive as solid. Farther out, water freezes. Beyond that, carbon dioxide settles, and in the far cold, carbon monoxide and nitrogen fall silent onto particles like rime on a window. These fronts are not just markers, they are factories that change the weight and stickiness of grains. Where ice appears, solids multiply, collisions become glue instead of shatter, and a quiet acceleration begins. The water snow line matters most for building large bodies quickly. Ice multiplies the mass available by a factor that feels generous, and it increases the size at which pebbles resist bouncing. The result is a belt where pebbles drift inward and pile up. Gas in a disk does not orbit quite as fast as Kepler would prescribe, because pressure supports a small fraction of weight, so pebbles feel a headwind and spiral toward the star. At a snow line, the sudden change in composition modifies that headwind and builds a pressure bump. Drifting solids slow and collect there. The pile is a soft trap where small objects become large ones by steady addition rather than violent smash. Cores form with ease, and a few reach the threshold where their gravity perturbs the gas enough to carve a shallow groove. Another front comes from chemistry that is less obvious but equally potent. When carbon or oxygen carriers condense, the remaining gas shifts its ratios. A planet that forms outside the water snow line and then migrates inward may wear a different carbon to oxygen stamp in its atmosphere than one born inside. A world that gathers its air beyond the carbon dioxide line and finishes closer to the star will carry clues to that journey in the relative heights of infrared bands. The snow lines write not only where mass sits, but also how flavors of air assemble. Those flavors endure and turn into quiet diagnostics that instruments can read without raising their voices. Migration owes as much to gentle talks as to dramatic kicks. A small planet embedded in gas launches spiral waves. One pattern pulls outward, one inward, and the imbalance between them sets the direction of drift. Temperature and density gradients tilt the equation. Near a snow line, opacity and entropy change. That change can flip the sign of the torque, converting an inward drift into a pause or an outward stroll. The region becomes a planet trap. Bodies that come wandering meet a place where the forces balance. Instead of plunging all the way toward the star, they stop and wait for the gas to thin. This waiting fosters calm. Crowds of protoplanets loiter near different traps and avoid close approaches that would otherwise end in scattered orbits. As planets grow, they reach the pebble isolation mass. At that threshold, a forming world perturbs gas enough to create a local bump that halts the inward rain of pebbles. Growth slows, and heat from contraction declines. The world cools into a state that can accept gas more slowly or simply stay as a heavy core with a modest envelope. When several bodies reach this point at different snow lines, a soft architecture emerges. Each one sits near a ring. The corrotation torque keeps positions stable, and orbits circularize under the damping of gas. The sharpest potential collisions fade into distant possibilities. The disk itself acts as mediator and tutor, asking worlds to take their places and keep them. With time, the star brightens slightly, and the snow lines move outward. The rings are not fixed paint. They are edges that drift with the slow change in stellar light and with the decline of gas as winds and radiation erode the disk. As fronts migrate, they carry the pressure bumps with them like rakes through a garden of pebbles. Planets tied to these features can slide as well, a migration that is smooth and reversible, more a tide than a shove. By the time the gas thins to transparency, the heavy lifting is over. Worlds have found their lanes. Some sit just inside former snow lines, others between them, where leftover solids are sparse and the risk of later chaos is reduced. Debris remains, yet its dance quiets. In the absence of gas, small bodies continue to collide, but the rate declines as the largest objects clear their neighborhoods. Resonances with the new planets shepherd fragments into arcs and gaps. Edges of belts emerge where secular frequencies discourage lingering. Through steady attrition and gentle guidance, the system gains soft borders. The inner region holds a modest occupancy. Farther out, a broad ring persists, but its inner edge is trimmed by migrators that moved until a resonance stopped them. These edges are not cliffs. They are gradients, where the likelihood of encounters drops smoothly, like surf reducing itself to ripples as it meets a shallow shelf. Snow lines leave imprints on the distribution of sizes as well. Inside the waterline, rocky super-Earths and mini-Neptunes often gain mass until gas disperses. Outside, cores can jump more quickly to the threshold for capturing thick envelopes. The difference sets a tone for the system. Warm inner orbits fill with small to mid-sized planets that damp one another into near circles. Cooler outer orbits pick up giants that hold distance and lend a slow guidance through resonances rather than through impacts. The presence of a giant far out can even protect the inner calm, deflecting late comets and keeping the compact family free from rattle. The geometry complements itself into a picture where calm propagates from ring to ring. Rings and gaps seen in young disks underline this story. Millimeter waves reveal bands where dust is thin and others where it is thick. Some gaps likely mark planets, but some align with chemical fronts and ice lines. At those lines, the optical properties of grains change. Icy aggregates grow larger and feel the gas differently. The subtle shift sorts particle sizes and creates structure even without a planet. These natural bands guide pebbles into safe lanes and increase the chance that forming bodies will not crowd. As the disk matures, planets and chemistry conspire to widen the differences. The final state carries a memory of its youth in the spacing of orbits and the scarcity of close approaches. Soft edges extend inward as well, sculpted by magnetic forces near the star. The inner cavity where gas couples to stellar fields truncates the disk and creates a final trap. Planets drifting close halt there, ending up with short-period orbits that respect a minimum distance. They avoid falling into the star because torques reverse sign near the truncation point. Trains of planets can stack just outside this boundary in compact, orderly arrangements. Once the gas goes, tides take over and round any leftover eccentricity into benign values. The inner system then presents a tidy set of worlds that rarely threaten each other. Time after gas dispersal brings a last round of polishing. Planetesimal-driven migration can slide giants outward by small amounts as they scatter remnants, while the inner planets accrete stragglers and damp their motions. Collisions still happen, yet most are glancing and most occur early, thinning rapidly as reservoirs empty. Eccentricity distributions narrow, inclinations relax. The long-term routes left open by the architecture are those that precess slowly without crossing paths. The dynamic temperature cools. Chaos zones shrink until they are small stripes that do not overlap with populated tracks. The outcome is durable. Snow lines also influence climate potential long after formation ends. Worlds that formed near the waterline often carry abundant volatiles. If they migrate inward just enough to warm those stocks, they may keep oceans without requiring deep atmospheres. Others born far out can retain hydrogen and helium with grace, smoothing temperatures under thick skies even at modest insolation. The original positions relative to ice fronts determine what materials are present to act as thermal buffers. That inheritance means the same star can host both a bare rock and a gentle ocean world, each calm in its own way, each a child of a different ring in the natal disk. There is a quiet artistry to edges that are not sharp. They guide rather than demand. A pressure bump stops drift without wreckage. A resonance shepherds without collision. A migrating snowline writes broad strokes that planets can follow. Afterward, debris thins by attrition instead of by catastrophe. The architecture that grows from these processes has the look of a coastline drawn by a patient tide, curves where material gathered, bays where it retreated, bars that formed to break waves before they met the shore. A listener can imagine the scene during youth: frost creeping outward as the star settles, pebbles flowing inward, slowing and piling at each front. Protoplanets lodging at the piles, exchanging angular momentum with gas, and finding orbits that make room for neighbors. Later, gas fading and leaving the lanes intact. Dust grinding quietly in the outer cold, lighting the dark with a soft glow that betrays the presence of a belt rather than a storm. Not a single moment shouts. The calm comes from the sum of many gentle interactions, each one small, each one in the same direction. Edges born from snow lines endure by becoming part of the geometry. They define where growth was fast and where it paused. They set the first chords of resonance. They leave the inner family circular and the outer family watchful. In that geometry, collisions fade to memory and orbits trace paths that return precisely. Planets keep their distance not by accident but by the quiet structuring of a disk that cooled, condensed, and thinned with elegance. The soft edges are the calmest facts of all. They allow a system to become a place where worlds can be slow, where seasons can be trustworthy, and where sleep can find a reflection in the sky. The balance that sustains life is not an accident of chemistry but a long conversation between energy and restraint. A world can host life only if it learns to moderate itself to breathe heat in and out without breaking rhythm. Too much light, and its oceans vanish into air. Too little, and those same oceans turn to stone. Between those outcomes lies a band of delicate compensation. Biology, if it takes hold, deepens that balance instead of disturbing it. Its work is quiet yet transformative, a process of feedback loops that keep temperature, composition, and circulation within bounds that last. Consider a planet wrapped in water and air. Sunlight warms its surface, water evaporates, and clouds rise. Those clouds reflect light, cooling the ground, but they also trap infrared, keeping nights from freezing. The mixture of these opposite effects finds a level that steadies climate. Vegetation, or its equivalent, draws carbon dioxide from the air and locks it in stone or biomass. Volcanism returns a fraction of that carbon through time. The rate of each act responds to temperature. When a planet warms, weathering quickens, pulling more carbon from the air and dimming the greenhouse. When it cools, weathering slows, carbon accumulates, and the air thickens again. The cycle is slow, but its direction is always toward restoration. It is a biological heartbeat coupled to geology. Life adds pigments that catch light, but also change albedo. On a world covered in photosynthetic layers, whether green, red, or some other spectrum chosen by a local sun surfaces become active sensors. They darken slightly when starved of energy, absorb more warmth, and brighten again when energy returns in excess. Each pigment family writes its own version of homeostasis. The changes are measured in percentages, yet they guide climate more gently than the most careful thermostat. Where seas freeze, the mirror surface chills the air, but once thawed, darker water drinks light again, pulling the planet out of its icebound state. A planet learns to use reflection and absorption as levers for comfort. In carbon chemistry, moderation arrives through the slow exhalation of volcanoes and the patient inhalation of rain. Each drop of water that falls carries a trace of carbonic acid, eating rock grain by grain, carrying ions to the sea where they settle as carbonate stone. Over millions of years, continents sink these stores and recycle them through the mantle. Outgassing at ridges returns them in equal patience. The result is a partnership between planet and sky, a dialogue in which surface temperature sets the pace of the exchange. As long as that conversation continues, neither fire nor frost can dominate for long. Nitrogen cycles play a quieter but equally essential role. Bacteria, if present, fix it from air into forms that feed life, then return it when organisms decay. The total mass of nitrogen in the air sets the blanket's thickness. Too thin, and heat escapes quickly. Too thick, and water remains vapor instead of rain. The biosphere adjusts this, albeit indirectly, by the speed at which organic matter turns over. On alien worlds, the same principle could operate through different chemistries: hydrogen and sulfur instead of oxygen and nitrogen, methane and ammonia instead of water and carbon dioxide. The shapes of molecules change, but the feedback idea remains: the community of reactions that damp perturbation rather than amplifying it. Some of the most calming features of life's influence are its tempos. Short events are local, long processes are global. A single storm is noise. The combined evaporation of forests is a pattern. A pulse of eruptions may darken the sky for years, but the biosphere answers with persistence, adapting albedo, changing mixing ratios of gases, and cushioning extremes. Over generations of living matter, the climate remembers the mean, not the moment. It drifts but rarely tips. Planetary rotation and the presence of continents shape these conversations. A fast spin spreads heat by breaking wind cells into bands. A slow spin merges them into a single circulation. Continents interrupt the flow, giving rise to monsoons, deserts, and green belts. When life covers these terrains, it modifies humidity and albedo locally, which in turn changes the wind. Every leaf, lichen, or analog changes the equation for radiative balance a little. The aggregated result is weather that learns the contours of its own home. On planets without life, feedback still exists but lacks subtlety. Runaway greenhouse or global freeze can end in stillness. With biology, every system gains new gears. Microbes release gases that form hazes, shielding the surface. Plants or their counterparts fix carbon, controlling atmospheric opacity. Even hypothetical chemistries of silicon or sulfur could establish cycles that regulate rather than accelerate change. The physical principle is universal. Reactions that depend on temperature often create stability if their rates are tuned to the right slope. The presence of metabolism simply expands the menu of stabilizing loops. This self-regulation can extend to oceans. In a water world, mixing carries heat downward and currents transport it poleward. If ice begins to grow, the salinity beneath it rises, driving heavier water to sink and pull warmer water upward. That convective turnover resists complete freeze. If the planet warms, stratification increases until deep layers isolate and slow the rise of additional heat. The sea becomes its own buffer, a dynamic lid that refuses to yield completely to either extreme. Over aeons, this feedback weaves into biological patterns. Plankton blooms that whiten the sea and reflect light during high insolation, or chemical releases that seed clouds when the surface grows warm. Every planet that harbors complexity must discover a balance point between internal heat and external light. Too much radiogenic energy, and tectonics rage. Too little, and the crust stiffens into silence. Yet even here the quiet tendency appears. As radioactive isotopes decay, heat production falls naturally, softening activity as time passes. The frequency of major resurfacing events declines. Volcanoes shift from fountains to slow exhalations. The geologic breathing slows until it matches the needs of the surface above. If life exists, it takes that stability and builds upon it. If not, the stillness itself becomes a serene equilibrium, the kind that lasts for billions of years. In dense atmospheres, lightning feeds nitrogen chemistry, and storms create pathways for water to reach high altitudes where ultraviolet light splits it. Hydrogen escapes, oxygen may linger. Too much of this escape, and the air turns oxidizing enough to limit further loss. Again, balance through reaction. Planets evolve regulatory ceilings, thresholds beyond which further change is self-limiting. The concept has no moral intention, yet the result is comfort. Boundaries appear without decree. Energy from the star also fluctuates on its own cycles. Spots and magnetic oscillations change brightness slightly. Thick atmospheres with oceans or high specific heat respond sluggishly. That delay ensures that short variations average out before reaching the ground. Only slow, million-year drifts in stellar output call for new equilibrium, and by then tectonics, biology, and chemistry have already shifted to accommodate them. The overlapping feedbacks build a layered defense against disorder. The pursuit of balance does not imply perfection. Some worlds will overshoot, finding themselves in glacial quiet or in humid heat that never relents. Yet even those states may stabilize into patterns of their own. Ice worlds reflect so much light that further cooling slows. Steam worlds build clouds so dense that radiation balances absorption. The galaxy may hold countless examples of equilibrium dressed in different temperatures and compositions. Each is a demonstration that physics favors endurance when left to run long enough. On the most forgiving worlds, life may even amplify serenity intentionally, or rather, as a byproduct of its appetite for consistency. Trees or their analogues release vapors that seed clouds above forests, ensuring rain where it is needed. Microorganisms generate gases that preserve surface pressure within limits. In doing these things, they create their own weather insurance. The biosphere and the environment lock into reciprocity, and what follows is long peace. A viewer far away might not see life directly. They would see steadiness. A planet whose light curve shows modest seasonal swings, whose spectral lines of carbon dioxide, methane, and water vary in ratio but never disappear, whose albedo shifts within a small range, these are signs of homeostasis. From a distance, such regularity reads as a lullaby. The planet turns, breathes, exhales, and takes another breath. The record of its light becomes a smooth wave, soft and dependable. The most calming truth in these balances is that the universe does not need noise to sustain richness. Stability is not silence, it is rhythm. The interplay of star, rock, air, and living chemistry finds its measure and stays near it, century by century. Planets that reach that state are not frozen in time. They are ongoing negotiations between change and its limits. Somewhere under another sun, a world may already have mastered this art. A world where climate hums rather than roars, where seas mirror skies that repeat, where balance itself is the form of life. Tranquility in the cosmos does not arise from luck alone. It can be described by equations, steady states written in the mathematics of motion, heat, and light. Scientists have begun to model these states, searching for the conditions under which a world can remain calm for spans measured not in decades or millennia, but in billions of years. They call these stable regions attractors, where a system, no matter how disturbed, returns to familiar ground. In these models, calm is not the absence of energy. It is energy arranged so that disturbances dissolve into order. One family of theories describes secular resonances that act like the tuning of an orchestra. In a planetary system, each orbit precesses, its ellipse slowly rotating through space. When the rates of those precessions align, the bodies exchange eccentricity and inclination in long cycles. Some alignments are destructive, pumping orbits into instability. Others are constructive, keeping eccentricities low and inclinations mild. Over eons, gravitational nudges can average out, leaving planets in self-regulating motion where energy trades hands but never causes harm. Mathematicians describe these as stable islands, in a chaotic sea regions where gravity's competing notes produce harmony instead of noise. Another set of models explores climate attractors. These are equilibrium points in planetary energy balance where radiation in and radiation out find equal footing. On Earth-like planets, feedback from clouds, ice, and greenhouse gases sculpts several such attractors: a frozen state, a temperate state, and a runaway greenhouse state. The temperate one, narrow but real, acts as a cradle for long life. Worlds that wander close to it can be nudged inward or outward, yet feedback forces gently pull them back. The discovery that these attractors persist under a wide range of stellar types is one of the quiet triumphs of planetary science. It suggests that serenity, once achieved, is not easily lost. Tidal equilibrium adds another dimension. When a planet slows until its rotation matches its orbit, the energy exchange between spin and orbit stops changing sign, heating declines, eccentricity falls. The tides become steady background motion rather than friction. The mathematics of this process describes a sink where rotational and orbital energies drain toward a final, balanced state. Some call it tidal lock, others prefer tidal peace. Once reached, the pattern is remarkably durable, shifting only as the star evolves, or as outside influences apply new torques. The equations show that most close worlds will reach this resting condition long before their suns fade. In the language of celestial mechanics, stability is measured by Lyapunov, times the interval before two neighboring trajectories diverge noticeably. In chaotic regions, those times are short. In orderly ones, they can exceed the age of the system. Numerical experiments integrating orbits of real exoplanet systems show many with immense Lyapunov times, meaning their present configurations will hardly change for eons. The orbits oscillate slightly, like a pendulum moving through thick air, but the amplitude remains small. What looks like motion from above is really a vibration around an equilibrium that repeats endlessly. Climate models employ similar logic with energy instead of motion. The equilibrium temperature of a world depends on its albedo, greenhouse effect, and internal heat. By adjusting these parameters, modelers find points where the derivative of temperature change with respect to incoming flux is zero, a stable slope. Disturb the system, add light, remove light, and it returns toward the same value. Beyond this slope, instability lurks, but within it lies the broad region of comfort where temperature variations damp themselves. In that regime, even large swings in stellar activity produce only modest atmospheric responses. Worlds resting there are thought to breathe slowly, their days and nights linked by gentle currents that refuse panic. In the study of atmospheric dynamics, the concept of attractors becomes visible through circulation patterns. The Hadley cell, for instance, acts as a regulator, distributing heat from equator to pole until temperature gradients reach a critical value. Once that value is reached, new cells form, redistributing energy again. The planet thus builds a self-limiting structure. Convection rises only until it smooths its own fuel source. Large-scale waves in the jet stream operate under similar logic. They amplify until they exhaust the temperature contrast that drives them. The winds themselves enforce balance by reducing their own strength. Long-term climate evolution is governed by feedbacks on geological timescales. The carbonate-silicate cycle remains the prime example, but others join it. Methane released by microbes increases warming. Warmer oceans dissolve less carbon dioxide. Less dissolution allows cooling to reverse. Each component acts as a spring around equilibrium. Computer simulations that include these loops show that a wide array of starting conditions converge towards similar moderate climates given enough time. The outcome is robust. Once life begins to interact with rock and air, it tends to create its own continuity. Theoretical biogeophysics predicts not the survival of all life, but the persistence of habitable conditions over astronomical time. Another theory explores the concept of climate attractors under chaotic, forcing how even random fluctuations can produce order when feedbacks are negative. This principle, known as stochastic resonance, allows a planet's climate to oscillate within narrow bounds rather than wander freely. Randomness becomes part of stability, a paradox that fits the quiet temperament of the cosmos. Noise rearranged into pattern. Under these conditions, no external disturbance remains strong enough to overturn equilibrium. Variations become texture rather than threat. Thermodynamic models examine entropy production in planetary atmospheres. A system far from equilibrium still seeks a steady rate of entropy increase, the maximum consistent with its constraints. In that steady state, heat flow, wind speed, and cloud cover adjust themselves so that the planet produces entropy as fast as it can without breaking structure. This state coincides with climates that maintain stable gradients and thus with conditions favorable to long-lived moderation. Even the second law of thermodynamics, when stretched over planetary scales, appears to prefer calm efficiency over violent waste. Orbital stability and climate stability intertwine. Eccentric orbits create strong seasonal contrasts, but tides and secular interactions tend to circularize them. Inclinations tilt slowly under the combined pull of companions, but large moons and stellar oblateness counter the drift. These mechanical dampers make sure that orbits do not slide easily into resonance that would disturb them. The probability of catastrophic chaos declines rapidly once a system's total angular momentum deficit falls below a certain threshold. Many observed multiplanet systems occupy exactly that regime, an empirical proof that nature selects low-deficit configurations as survivors. Mathematical theorists extend these ideas into climate networks, webs of variables connected by feedback signs. When the majority of connections are negative feedbacks, the network resists perturbations. This model predicts a range of stable topologies, each corresponding to a climate type: water-rich, hydrogen, heavy, or cloud-dominated. The more negative links, the greater the resilience. Real planets discovered so far cluster near these resilient configurations, as if evolution of systems naturally climbs toward peaks of stability in a vast multidimensional landscape. Philosophically, these equations describe something comforting about the universe itself. Despite being governed by indifferent forces, it builds structures that endure. The same gravity that can destroy also creates gentle orbits. The same radiation that can strip air also drives the circulation that cools it. Stability emerges not because the universe is kind, but because the pathways of least energy are also the pathways of quiet repetition. Worlds that find those paths linger. Worlds that do not are erased. The cosmos prunes itself toward calm. A simple image conveys the essence. Imagine a marble resting in a bowl. Push it, and it rolls but returns to the center. Push harder, and it climbs the wall, hesitates, then falls back. Only if the shove is immense does it escape entirely. Most planets, once they cool and settle, behave like that marble. Stellar fluctuations, impacts, migrations all act as pushes. Yet for many, the bowl is deep and the shoves are small. The result is persistence that outlasts memory. Astrobiologists see in these theories a form of optimism. If calm is an attractor, then it should recur across the galaxy. Given enough attempts, worlds will slide into those basins of stability where time and chemistry can cooperate. Even without direct evidence of life, the existence of many long-lived equilibria suggests that the universe favors continuance. The laws of physics lean toward endurance, not eruption. At the farthest level, this tendency becomes a meditation on time. Stars flare and fade, galaxies collide, yet between those dramas, equilibrium reigns. A planet circling a quiet star can remain clement for billions of turns, carrying its oceans, winds, and clouds through epochs without forgetting their rhythm. The equations predict it, and the data begin to confirm it. From those truths arises the most tranquil theory of all, that serenity is not a brief interval between storms, but the natural destination of systems allowed to evolve. When telescopes began to see not just dots but atmospheres, the silence of the cosmos grew articulate. Every spectrum recorded by a mirror and grating became a line of dialogue between a distant world and the instruments that listened. The new generation of eyes, spaceborne and groundborne, turned their lenses to the faint glows of exoplanets and found that calm could be measured, that tranquility itself left fingerprints in light. To listen with new ears meant not only hearing sound but interpreting radiance as rhythm and data as music. The James Webb Space Telescope opened that quiet conversation in infrared. It gathered the heat of distant suns and sifted it through the delicate changes of wavelength that betray chemistry. Transmission spectra from transiting planets revealed water vapor, carbon dioxide, and methane, sometimes all within the same world. The lines were soft, not jagged. Their presence showed an atmosphere thick enough to balance day and night, and stable enough to last through many orbits. When the spectrum stayed constant across repeated passes, scientists saw it as a sign of equilibrium, a steady climate breathing under a gentle star. These observations spoke through faint ratios of light, fractions of a percent. Webb's sensors watched a star dim as a planet crossed and brightened again after the eclipse. The difference between the two spectra gave the planet's own glow, a whisper amid the roar of the star. In that whisper lived temperature, albedo, wind, and weather. On one hot Jupiter, brightness shifted slightly east of the substellar point, evidence of winds transporting warmth from day to night. On a smaller, cooler world, the same analysis suggested a muted phase curve, a sign that its air distributed heat smoothly. Where older telescopes saw only silhouettes, Webb heard the cadence of atmosphere. Back on Earth, the extremely large telescope began its watch with a mirror so vast it could split starlight into thousands of narrow channels. Adaptive optics bent distorted beams into clarity, allowing astronomers to see the small wobbles of spectral lines that betray rotation and wind. High-dispersion spectroscopy captured air in motion, sodium broadening near limb regions, carbon monoxide stretched by Doppler shift. These delicate distortions told of jet streams moving hundreds of meters per second, yet keeping patterns over years, a meteorological calm on worlds many light-years away. Star shades and coronagraphs followed, creating artificial eclipses that hid the glare of parent stars and left planets visible in reflected light. Direct imaging brought a gentler palette. Planets appeared as faint dots, shifting in arcs of light, their colors hinting at clouds and hazes. The next step was to split that color further, to read their compositions. Some reflected a clean blue from Rayleigh scattering, others a muted copper from aerosols, and a few carried the signature of methane absorption, soft valleys in the reflected spectrum that matched expectations for temperate skies. The precision was breathtaking. To isolate such signals required stability in every mirror segment and every vibration of machinery, a mechanical serenity designed to capture celestial serenity. Listening expanded beyond visible and infrared. Radio observatories tuned to frequencies where planetary magnetic fields may sing. A planet with a magnetic cloak interacting with its star releases cyclotron emission that drifts in frequency as it rotates. The signals are faint and require patience, weeks of data folded and cross-correlated, but when found, they hint at shields that preserve air and nurture stability. Even a weak detection tells a story. A core still molten, rotation still present, internal energy still circulating. Magnetism becomes audible proof that a world is alive in motion, even if silent in every other way. New sensors tested air by starlight polarization. As light scatters through a planet's atmosphere, its polarization angle shifts in patterns that encode cloud particle size and composition. Observations of these subtle changes revealed mists of ammonia, silicates, and water droplets suspended in calm layers. The way those patterns remained nearly unchanged between observations months apart suggested atmospheres that knew how to maintain their equilibrium. In such data, scientists began to hear not storms but long pauses, a steadiness that only billions of years could teach. Spectrometers on Webb and other platforms began to reach beyond detection into diagnosis. Variations in carbon to oxygen ratios offered clues to where a planet had formed relative to its star's snowlines. Low ratios implied origins beyond water frost fronts. Higher ones hinted at inner, drier births. The diversity painted a picture of systems arranged by chemistry rather than chaos. The more data accumulated, the more it seemed that each planetary family contained quiet order, a chemical architecture guided by early balance. The transiting Exoplanet Survey satellite, once the eyes of discovery, transformed into a monitor of consistency. It revisited the same systems, checking whether transits changed. Most did not. The constancy of timing meant orbital peace, no massive neighbors pulling at them violently. The tiny shifts that did appear told of distant companions or tides, regular and predictable. Each steady light curve became a record of endurance, an entry in the ledger of cosmic patience. Ground-based arrays like ALMA contributed by tracing dust and gas around young stars. They showed rings, gaps, and spirals so regular they resembled clockwork rather than accident. These were systems in formation, not yet planets but the scaffolding of order. Observers could almost hear the rhythm of growth, a tempo so slow it needed mathematical translation. The data were still young, but the patterns were already ancient in spirit, places where turbulence had given way to pattern, and pattern promised longevity. Beyond instruments, data analysis itself became an act of listening. Machine learning algorithms combed through spectra, identifying recurring features that the eye could miss. They found subtle periodicities, signatures of rotation periods, phase-locked climates, and stable cloud layers. The machines, trained on the physics of calm, recognized it wherever it appeared. Human researchers looked on as computers highlighted signals too quiet for intuition, teaching people to hear the universe's gentle side through artificial ears. Each success added to a portrait of normalcy that was, paradoxically, astonishing. Calm turned out not to be rare. Planets that repeat their transits perfectly, that hold atmospheres without wild escape, that reflect starlight in stable tones, these are common. The galaxy, viewed through instruments fine enough to detect whispers, revealed itself as an archive of endurance. Violent birth gave way to gentle maturity, and telescopes became witnesses to that long quiet. The next generation of instruments promises even softer hearing. Concepts like the Life Finder telescope and the Habitable Worlds Observatory plan to study biosignatures not through peaks of intensity, but through ratios that persist over time. Instead of searching for dramatic anomalies, they will look for stability. oxygen and methane coexisting for centuries, spectral lines that vary only within narrow margins, indicators of feedback rather than flash. The measure of life may turn out to be constancy. Listening with new ears means acknowledging that silence is information. A flat light curve can be as telling as a jagged one. A line that refuses to change is the signature of equilibrium. Every non-event recorded by a telescope becomes proof of a system's reliability. When astronomers compare these quiet datasets, they find harmonies between worlds separated by hundreds of light years. Each pattern, each lull, adds to the sense that calm is not an exception but a law written across creation. In the end, these tools do more than observe. They reveal the temperament of the universe. The data say that most stars host planets, most planets find orbits that endure, and many hold on to air, water, or balance for unfathomable spans. The cosmos, viewed through the patient glass of modern observatories, is not a battlefield of chaos but a collection of sleeping worlds, each one turning, breathing, and waiting. Through every wavelength of light, through every pixel of data, science learns the same lesson. To understand the universe, one must learn to listen quietly. The night side of the future is painted in soft colors. Humanity dreams of stepping beyond its native star and finding havens under other suns, not to conquer but to rest. Among the millions of orbits charted and modeled, a few stand out as invitations, worlds with gentle light, steady weather, and the kind of gravity that feels like memory. The vision is neither empire nor exile. It is a slow migration into quietness, a wish to live inside the calm that nature has already composed. To imagine that journey begins with small ships tracing routes through darkness. They would sail not on fire, but on momentum, coasting through gravitational lanes carved long ago by the same physics that governs planets. The trajectories would arc between stars where red dwarfs glow dimly and steadily. For centuries, travelers might sleep or their descendants might wake to find their destination brighter by degrees. Through thick windows, the first glimpse of another sun would not be a blaze but a pulse of amber in the black, promising warmth that does not rush. Arrival would unfold in silence. Engines cut, orbit found, and the new world rising beneath half-lit, half-dark, a round horizon with veils of cloud drifting in slow motion. The atmosphere would show its peace before a single step was taken. Stable color bands where no towering storms churn, a consistent albedo across seasons. Instruments would read wind speeds that change little from year to year, pressure profiles that hold steady, rotation that hums with the gravity of rhythm. The settlers, trained to expect harshness, would find instead a climate that greets them gently, a sky that behaves as if it has known patience for eons. Life there, if it exists, would probably move as slowly as the star that warms it. Photosynthetic organisms might open and close with tides rather than with days. Their pigments would lean toward the red, drawing strength from long wavelengths that sink deep into leaves or films. Rivers, if present, would carry a color that comes not from mud, but from chemistry, iron oxides or silicates, shaped by calm erosion instead of floods. The landscape would feel composed by time itself, not by violence. Hills worn down until their lines resemble the curves of orbit, valleys carved with deliberate understatement. In such a place, humans would build with the same restraint. Domes of glass or transparent composites would rest lightly on plains, powered by the steady light of a nearby sun that never blazes nor dims. Agriculture would follow the rhythm of slow days, adjusting to the eternal afternoon of a tidally locked world. Crops might grow under permanent dusk, nourished by the filtered glow of the red star overhead. There would be no sunrise, only a luminous horizon that circles the planet like a patient heartbeat. On the far side, under the night that never ends, observatories would look outward, studying skies unbroken by weather or city light. Communication between such colonies would unfold over decades, messages traveling at light speed but arriving to descendants rather than senders. Yet even that delay would fit the new temperament. Civilizations might learn to think in centuries, to measure success not by expansion but by continuity. The ambition would not be to change these worlds but to harmonize with them. Machines would hum quietly, managing climates and recycling air, designed to last as long as the star's steady output. The concept of progress would soften into the concept of maintenance, a philosophy of care, rather than conquest. A future written in gentle dark does not erase technology, it refines it. Solar arrays would spread like leaves, tracking the slow arcs of light with almost biological patience. Cities, if that is still the word, would merge with geology, borrowing heat from crust and cool from shadow. Energy demand would align with natural cycles. Artificial light would mimic starlight. Even art would follow this new tempo, paintings made of minerals that change color with angle, music tuned to the resonances of long days and short years. The culture born under such skies would know time not as urgency but as depth. Among the stars, each system would contribute its own version of peace. Around some, the tranquility would come from perfect rotation, worlds that turn once per orbit and experience perpetual balance. Around others, calm would arise from diversity moons exchanging light, gas giants shielding their children from cosmic rays, orbits that precess just enough to mix climates but never enough to ruin them. Every settlement, every observatory, every memory of migration would echo the same realization that serenity is the most sustainable state of matter. Human presence might even extend to floating habitats within the atmospheres of gas giants, where pressures match those of familiar air and the view extends in endless curls of color. There, science could listen to the thunder that never reaches the ground, studying electricity that repeats with clock-like regularity. Farther out, icy moons with internal oceans would host communities beneath domes of light reflected from their parent planets. Each environment would carry its own rhythm, and humanity's greatest adaptation would be learning to live in tune with it. Long after the Earth has quieted and its oceans have thinned, the descendants of its explorers may still orbit these calm stars. They will measure time in stellar pulses and migration in generations. To them, the galaxy will not appear as a wilderness but as a network of steady hearths, each one a sun with its own family of enduring worlds. They will know that chaos was the beginning, not the rule, and that the universe has always been working toward equilibrium. The evidence will surround them in every stable orbit, every balanced climate, every whisper of magnetic aurora that plays above a nightside sea. The imagination of that distant age does not need grandeur to feel infinite. It needs only stillness. It is easy to picture a moment when a person stands on a shore of another world, the light of its star painting the air in rose and gold. No wind, no noise, just the faint motion of clouds along the horizon and the pulse of their own heartbeat, keeping time with the planet's rotation. In that moment, there is no distance between discovery and belonging. The traveler realizes that calm was never merely a property of the world, it was an inheritance waiting to be recognized. The futures within the gentle dark are not fantasies of escape, they are extensions of what already exists wherever physics favors peace. To sleep beside new suns, to live within steady atmospheres, to breathe air that remembers balance, these will be acts of alignment, not defiance. The human story, stretched across light years, will at last find its rhythm within the universe's slowest music, and the cosmos, patient and vast, will welcome that harmony with the same quiet light that has always been its language. At the farthest reach of imagination lies a question that will not sleep. What, in the end, makes a world calm? The equations of gravity can describe orbits, the laws of thermodynamics can explain climate, but neither quite capture the feeling of peace that certain planets seem to emanate, the impression of stillness, the sense that time there moves not as a river, but as a tide. Some astronomers speak of equilibrium, poets might call it grace. Between those two words stretches a truth that both science and wonder attempt to hold. A planet is calm when its contradictions coexist without struggle. Heat and cold, day and night, pressure and release, all balanced, all perpetual. Its star feeds it light, but not too much. Its core stirs with energy, but not too fast. Air flows, but does not rage. Water moves, but does not devour. From afar, such a planet looks unremarkable, yet the smoothness of its light curve, the regularity of its motion, the constancy of its temperature, all reveal a perfection born of patience. Calm, in physics, is a state of minimum change per unit of time. In philosophy, it is the realization that perfection and motion can live together. The universe, in its vast laboratory, seems to favor this middle ground. Systems that flare or freeze rarely last. Those that balance linger. Over billions of years, chaos spends itself. Dust settles into disks, disks into planets, orbits into steady repetition. Even the violence of formation is only a prelude to order. Galaxies collide, yet stars rearrange into new spirals. Stars explode, yet their remnants form the seeds of future suns. Across this endless sequence, one can sense an underlying drift toward gentleness, as if energy itself, through endless exchange, learns restraint. To gaze into that pattern is to glimpse a deeper symmetry, the way life, physics, and time share an instinct for moderation. Every living cell regulates its temperature and chemistry. Every stable orbit finds a resonance that prevents collision. Every long-lived star maintains fusion at the exact rate that keeps it from collapse. Perhaps calm is not a state but a principle, an attractor woven into the architecture of the cosmos. From hydrogen clouds to human thought, everything that endures learns to balance inward pull and outward push. Survival itself is serenity practiced. When scientists model distant planets and find ones that hold oceans for eons, they are not merely predicting climate, they are watching harmony express itself in mathematics. The energy that could have produced storms instead sustains cycles. The feedbacks that might have amplified extremes instead cancel them. It is as if each system carries its own instinct to remain within bounds, an ancient reflex written in the equations of motion. In that sense, calm is a universal language, older than life, older than light. Yet calm is not absence. It is structure so complete that it seems silent. In every molecule of air, collisions continue. In every orbit, gravity hums. Stillness is an illusion born of scale. What feels serene is, in truth, a dance so precise that its steps repeat forever, without correction. The serenity of a world, then, is the sum of motions so balanced that they appear at rest. A sunset seen from its surface might take hours to unfold, clouds shifting like slow brushstrokes, shadows stretching with the deliberation of thought. The beauty lies not in inactivity but in continuity. If one were to stand on such a planet, a sphere turning under a small, patient star, the calm would not come from silence but from repetition. Waves would roll with mathematical consistency. Winds would whisper the same phrases across centuries. Night would return with such precision that calendars could be carved into stone and never lose accuracy. The soundscape would be low and cyclical, a chorus of pressure, a soft equilibrium of motion. The listener would feel their heartbeat begin to match the pace of the sky, a resonance between biology and orbital mechanics. Perhaps this is the final connection, that calm, wherever it appears, invites recognition. A stable world is not merely a physical curiosity, it is a mirror. It reminds its observers that they too are patterns seeking balance, storms learning to slow. The mind that contemplates serene worlds begins to absorb their rhythm. To study a steady light curve is to feel one's thoughts smooth out. To trace the shape of a stable orbit is to glimpse how a life might revolve around its own quiet center. Astronomy becomes meditation, and physics becomes prayer. For all its violence, the universe does not shout forever. It learns, through its own mechanics, to whisper. Stars fade into dwarfs that will burn for trillions of years. Collisions become orbits. Explosions become dust. Dust becomes the soft glow of nebulae that will one day condense again. Eternity, it seems, is not filled with fire, but with balance. The cosmos, if given enough time, tends toward gentleness. This is not sentiment, it is entropy interpreted as peace, the long smoothing of differences until even light moves evenly through the dark. And so the question circles back. What makes a world calm? The answer, perhaps, is that calm is the final product of everything else. It is the natural conclusion of energy-seeking symmetry, of gravity finding rhythm, of life learning restraint. Calm is the oldest outcome, the one written into the fabric of existence before the first atom cooled. Every orbit, every climate, every mind that finds rest is repeating the same gesture, the desire to continue. In that understanding lies the quiet heart of the cosmos. Every exoplanet discovered, every line of light passed from a distant sun adds to the evidence that stillness is not rare. It is the rule that chaos briefly forgets. The universe does not end in noise. It settles, patiently, into balance. Somewhere, beneath a soft and endless sky, another world turns in silence, and that silence is the sound of time at peace.